This one says, consider the statement below. The perpendicular force exerted by a surface on an object in contact, and then it says which one of the following is defined by the statement above. Alright, so we know from Newton's laws and things like that, that if you have, for example, if you have a surface, right, so you've got a surface over here, and you've got this object, and if I had to ask you to draw a free body diagram, well, you would say that there's gravity, and then you would also say that there's a normal force. Now, the normal force is the force exerted by the surface on the object. So it says here, the perpendicular force exerted by a surface on the object. So this answer would definitely be A, which is your normal force. Two balls of masses m and 2m are dropped simultaneously from the same height above the ground. When the balls strike the ground, which one of the following physical quantities will be the same for both balls? Well, you see, so here's where things can sometimes feel a bit weird, because logically, right, if we think about this in real life, many of us would say, oh, the ball that has a mass of 2m is definitely going to hit the ground before, or it's going to hit the ground first, right? It's going to hit the ground before the ball with m. The same way, if, for example, we had a little building over here, that's a very straight building, Kevin, maybe it's the Leaning Tower of Pisa, and then let's say, for example, we had a little feather. Okay, so we've got this little feather. Now, I'm not going to try to draw. I'm not going to pretend that my goodness. So that's my idea of a feather. But most people would maybe say that that's like a rocket, or it could even be like a little mouse. I don't know, but that's my feather. No judgment, please. And then I'm going to draw an elephant. Okay, I'm not going to draw an elephant because if I can't even draw a feather, imagine what an elephant would look like. Okay, so let's say I draw a big, heavy ball. Okay, but like this ball's really heavy. Okay, it's made of steel, so it's very heavy, and this is a feather. Now, if you had to go ahead and drop both of those, we know just from being alive, we know. And the way that the earth works and the way life works is that this ball is going to definitely hit the ground first. So this leads us to believe that heavier objects always hit the ground first. Now that is correct, but that is only because of air resistance. Air resistance is playing a major role in that. But in grade 12 physics, and in most high schools around the world actually, we don't take air resistance into account. I'll prove it to you. Or let me first say that the mass is not, the heavier object is not going to necessarily hit the ground first. Even if we look at all of our equations of motion, you know, the ones that are like Vf squared equals to V initial squared plus 2a delta x or 2a delta y, whatever you prefer. We've got these other ones. I don't know about you, but I can't see anything that tells me I need to look at the mass. There's no mass in any of these formulas. All that it needs is the initial velocity and the acceleration, which is 9.8 for all of these objects, and the distance or the displacement and the time, but there's no mass. So what that means is that whether we have an object that is mass m or 2m, they are both going to hit the ground with the exact same velocity. Okay, because if you had to use this formula over here, for example, you can just imagine that both of the initial velocities are going to be 0 because they dropped. A is a constant for all objects on the surface of the Earth, 9.8, and then x would be the displacement or the distance or the length of this building. So you would notice that the velocity, the final velocity, would then be exactly the same for both objects. Now, I know for a fact that some of you are like, yo, well then, Kevin, what about the kinetic energy? Why is that going to be different? Why is the momentum going to be different? So that's because of mass, guys. So momentum we know is equal to P equals to mv. So we know that the velocity would be the same at the bottom, but the masses are going to be different. So the heavier object will have a larger momentum. Okay, so it can't be that one. And then what about the weight? Well, the weight is equal to mg, so that won't be the same because m is different for both objects, and kinetic energy is half mv squared. So once again, the masses are not the same, but the velocities will be the same, so the kinetic energy will be different. So the answer for this one is B, which is velocity. The graph below shows how the momentum of an object changes with time. Then it says, during which one of the following time intervals is the magnitude of the net force the greatest? Okay, so the magnitude of the net force. So we need to definitely find a formula that uses net force. So the only formula for net force, if we had to look on our formula sheet, would be probably this one over here that also uses momentum. So we can say F net is equal to the change in the momentum, okay, over the change in time. Now, in each of these answers, can we see that the time is 1 second? Because, I mean, this is 0 to 1, that's 1 second. 1 to 2 is 1 second. 2 to 3. So the time is only going to be 1 second. So let's just get rid of that. Because if we divide by 1, that's not going to do anything. So we can sort of look at it like this. Okay. So what this tells us then is that the time interval with the largest F net is going to be where the change in the momentum is the largest. So let's go explore 0 to 1. So 0 to 1, we're going from 0 up to 20. So what is the change over there? Well, the change over there is going to be 20. Now, if we look, when we go from 1 to 2, and we don't have to worry about negatives and positives here, guys. We don't have to worry about the direction and stuff. I'll tell you now what I mean. So like from interval 1 to 2, we're going from 20 to 10. So how much are we changing by? We're changing by 10. Don't worry about saying negative 10 or whatever. It's just going to be 10. We're just trying to see the biggest size. And then for the next one, we're going from 2 to 3. So that means, okay, so from 2 to 3, at 2 we are at 10, and then at 3 we are at negative 10. Now you got to be careful. If you go from 10 to negative 10, that's a change of 20, right? If you're going from 10 all the way to negative 10, that's a change of 20. And then the last one is 3 to 4. So that's going from minus 10 up to 20. So that would be a change of 30. So it says, during which time interval is the magnitude of the net force the greatest? Well, it would be when the change in the momentum is the greatest. And so the answer for that one is D. A ball is dropped from a height above the floor. Okay, so I like to always just make a little picture. So a ball is dropped from a height above the floor. So let's quickly draw the floor. Let's draw the ball. And we know that that ball is being dropped. Okay, dropped implies that it's got an initial velocity of 0. Okay, the ball makes an elastic collision with the floor. Okay, so when something collides elastically, it means that it will hit the ground and then it will bounce up to the exact same height. Why? Because no energy loss takes place. If you have an elastic collision, there's no energy loss. Right. So it says the ball makes an elastic collision with the floor and bounces vertically up. Ignore air resistance. Which one of the following graphs shows how the total mechanical energy of the ball changes with time? Okay, so we should know that objects have two types of energy, right? There's always kinetic, or they can be kinetic, and they can be potential energy. Okay, kinetic is due to speed, or the velocity, and this one is due to height. If you add these two together, if you add the kinetic energy and you add the potential energy together of an object, we call that the mechanical energy. That is what mechanical energy is. It's the sum of kinetic and potential energy. We should also know that mechanical energy is conserved, meaning that it doesn't change, unless there are non-conservative forces like friction, applied forces, tension, and things like that. But in this object, or in this system, there is no external forces from the top to the bottom. Okay, at the bottom there is going to be a little bit of a force because of the floor, but we'll talk about that now. And then on the way up, there is no external forces. So the mechanical energy should remain constant at that part and at that part. So I know some of you are probably saying, oh, well, then the answer should be this one over here, Kevin. Or maybe this one over here, but that's not true. The mechanical energy needs to remain constant. So it's constant over here. See, it's constant. It's not changing. Like if this is 10 joules, then it remains 10 joules. Then what happens is that when it hits the ground, the mechanical energy actually goes, it would probably go down to 0, to be honest. Because for that split second, that split second that it's hitting the ground, it's going to have no velocity, and it's also going to have no height. So for that split second, it would have no mechanical energy. And that's why we're seeing like a sudden drop off, but then instantaneously it comes back up again and then carries on. And so the answer for this one is definitely going to be B, because the mechanical energy remains constant. During this part of the motion over here, when it's going down, what happens to the kinetic energy? Well, that goes up, right? Because the object would get faster. But what would happen to the potential energy? Well, that would go down because it's getting lower down. And so the kinetic energy is going up, but the potential energy is going down, but the mechanical energy should remain constant. And then on the way up again, the potential energy will increase because it's getting higher up, but the kinetic energy would get less because it's going to slow down as it goes up. But if you add the potential energy and the kinetic energy for this part, it should remain constant. And so we're looking for the one where the mechanical energy is constant for most of the duration, except for when it hits the ground over there, where it has a little drop and then it comes back up again. But it happens literally instantly. All right, and so the answer for this one is B. Consider the two spectrum diagrams below. Okay, so we have a diagram 1 and a diagram 2. We've got blue and we've got red, and then we've got some lines. It says that diagram 1 represents the spectrum of an element on Earth. Diagram 2 represents the spectrum from a distant star as observed from Earth. Okay, so this one here is from a distant star. And then, but it's being observed from Earth. I'll explain this now. Observed from Earth. And then this one, the top one, is in the laboratory, in the lab on Earth. Alright, so before we go into this question, I need to give you a quick summary and a quick recap of this whole idea of the blue shift and the red shift, and some scientists are saying that the Earth is busy expanding and all of that. And it all has to do with the Doppler effect. So let me quickly explain. Let's say we have a planet, and let's call it planet Earth, because I would imagine that that's probably the most appropriate for most of you who are watching this. If not, hey E.T., hope you're well. So here's the Earth. Okay. Now let's go back in time. Let's tell a story. Let's say we are back in the year 2015. Okay, so we're in the year 2015, and we've got this little star over here. Oh my goodness, Kevin. I thought I was trying to be cool there. Okay, so that's the year 2015, and we have a star. And we've got a guy, or lady. Come on, Kevin, it's the 21st century. We can't be doing stuff like this. So we've got a person standing over here. Okay, and they've got a little machine. Okay, so they're holding this little machine. Let's say the machine looks like this. Okay, and what this machine does is, okay, so what happens first is that the star is releasing light. Okay, so that light is going to travel to the little machine, and that machine is going to measure the frequency of the light. Okay, so this machine is going to measure the frequency of that light. And let's say in the year 2015, the frequency is measured as 200 hertz. Okay, then let's fast forward to the year 2025. Okay, so let's say 2025. By the way, none of those years are the years in which I am recording this video. It's somewhere in between there. So don't think that this video is super old and I recorded it in 2015, and don't think that I'm like in the future recording in 2025. I've just realized that it probably doesn't matter that I needed to say that part. But anyways, let's carry on. So let's say it's now the year 2025. and we've got another person. Hope we'll still be able to call people persons by that time. So we've got a person, and that person also has a machine. Okay, the machine's a little bit more sophisticated, maybe, I don't know. But what's happening is that they also they also measuring the stars. Okay, maybe it's the same star, I don't know, but they're measuring the stars, and so that star then shines down, and in the year 2025, the frequency that star is that machine is detecting is only 140 hertz. So over the 10-year period, what is happening? The frequency that the stars are giving off is being measured lower. So as the years go on, the frequency that we're measuring from the stars is becoming less. So what is happening? Well, think about the Doppler effect. If you have the Doppler effect, when does the frequency become less? When the two objects are moving away from each other, or when the two objects are moving towards each other? Well, if an ambulance is coming towards you, you're going to hear a higher frequency, and when the ambulance is moving away from you, you're going to hear a lower frequency. So what is happening to the distance between the stars and the Earth? Well, not the distance, but is the star and the Earth moving away from each other, or is the star and the Earth moving towards each other? Because the frequency is becoming less, it means that the stars and the Earth are moving away from each other. Let's write that down. Star and Earth moving away from each other. It is for this reason that scientists are saying that the galaxy is expanding. So therefore, the galaxy the universe is expanding. Okay, so that's pretty interesting. So that's what they're saying, that the universe is expanding. Okay, that might not be what's happening in this question. This might be a made-up question, but I'm trying to make you have the understanding on how these questions work. Okay, so now where does the red and the blue come in? Okay, so that's a good question. Let's talk about red. Red is considered to be a very low energy type of light. It's got low energy, and it's also got very low frequency. Okay, and it travels like this. It's very chilled. It's like red's a really calm color. Like if red is the calm, relaxed color. Okay, then you've got blue. Now blue is crazy. Blue's high energy, high frequency. Okay, so blue's like this. Blue's like super crazy. Okay, so if we said that the stars and the Earth are moving away from each other, what is happening to the frequency? We said that the frequency is becoming less. So because the frequency is becoming less and less and less, is it starting to become more like a red light, or is it starting to become more like a blue light? Well done if you said it's becoming more like a red light, because that's becoming a lower frequency. So what scientists are saying is that there is a red shift that is busy happening, where the stars are releasing a lower frequency, and so we're shifting more towards the red. Okay, that, as I said, that might not be what's happening in this question, but that's what's happening in real life. Okay, so that's where the red-blue shift comes in. So let's see what's happening here. So on the Earth, here we've got 3 lines. See them? Now on this, now when you measure it from the star, then the 3 lines are still there. But look at where the 3 lines have gone. Have they shifted more towards the right-hand side, or have they shifted more towards the left? Well, if you look at that and you look at that, we can see that there is a shift going more towards the right-hand side. So from the star, we can see that it's shifting more towards the red, which means that the star is definitely moving away. Because remember, when things move away from each other, the frequency becomes less. So what we'll say here is that the star is moving away from Earth. So the answer for this question would be C. The diagram below shows the field lines for the combined electric field due to two small charges, P and Q. Which one of the following combinations correctly shows the polarity? Okay, so I just need to give you guys a quick reminder. When things are positive, the lines move away. And when things are negative, then the lines move towards. Okay, so let's rather do it this way, and then we do that. That's what you need to know. So this is an easy question. So if you look at P, you can see that the arrows are pointing away. So that means P must be positive. Okay, so P is positive. So these two cannot be the answer. Okay, so let's scratch out. Cannot be A and B. And then if you look at Q, the lines are going towards. So Q must be negative. So the answer here is D. Two identical spheres, P and Q, carry charges of Q and minus 2Q respectively. Okay, so let's quickly do that. So P is Q and Q is negative 2Q. Okay, and it says sphere P exerts an electrostatic force of magnitude F. Okay, so there's a force, sphere P is exerting a force F on Q. Then it says, which one of the following represents the magnitude of the electrostatic force exerted by sphere on sphere P by sphere Q? So they want to know what is the force of Q on P. Now guys, remember Newton's third law. When two objects, okay, so when an object A exerts a force on object B, then object B exerts the same force, but just in the opposite direction on object can't remember which one I said first. When object A exerts on B, then B exerts on object A. And that force is the same value. It's the same size. Okay? So the answer for this one is definitely B. There's no calculations that you need to do here. This is literally just Newton's third law. In the diagram shown below, all resistors are identical. Ignore the internal resistance of the cell. Which voltmeter will have the highest reading? Alright, so I'm going to start off by showing us the voltage formula. So voltage is equal to current multiplied by resistance. So I'm instantly going to try to convince you that this voltmeter is definitely going to be higher than this one as well as this one. Okay, let's explain why. Let's say we have 10 amps. Let's say we have 10 amps of current flowing out of the battery. So we've got a current of 10 amps. So how much current is going to go through this resistor? Well, 10 amps, right? Okay. Then you're going to come down here, and then we're going to hit the parallel combination. And what will happen is that because these two resistors are the same, the current is going to split perfectly. So 5 amps is going to go through this one. And then another 5 amps is going to go through this one. So how much current is going through this resistor? Well, 5 amps. So if you had to use V equals to I times R, you would be saying something like 5 multiplied by whatever the resistance value is. Okay? And then for this one, you would be doing the same. But for this one up here, you would be saying that the current is 10. Okay? But the resistance value is going to be the same as this one, and it's also going to be the same as this one. So if you had to multiply the current and the resistance, we should be convinced now that this voltmeter is definitely going to be larger than V2 and V3. Okay, so the answer cannot be V2 and it cannot be V3. So now we somehow need to compare V1 and V4. Now, how much current is going to go through V4? Well, V4 starts here and ends here. And we said earlier in our little random example that if this was 10 amps, then we said that 5 would go this way and 5 would go this way. But how much current is going from here to here? Well, that's still going to be 10 amps, right? Yes, some of it's going in the top branch and some of it's going in the bottom branch. But once it goes through here and it goes through here, it's going to combine to become 10 amps again. And that's going to go through. So 10 amps 10 amps is going through this part of the circuit, and 10 amps is also going through this part of the circuit. So now we need to compare the resistance values. So this resistor, let's say for example that this resistor was 2. Then this resistor would also be 2, and this resistor would also be 2. But to find out the total resistance for this part of the circuit, you would have to use the parallel formula. And so that would be 1 over 2 plus 1 over 2. And that would end up giving you 1 over 1. And then if you had to work it out, you would see that R parallel is equal to 1. So the effective resistance in this part of the circuit is only 1 ohm, whereas here it was 2. And we know that in parallel the resistance becomes less. So this part of the circuit has a lower resistance than this part of the circuit over here. Even though there's more resistors, because they're in parallel, it drops the total resistance. So this one, if we had to work out this one's voltage using our random little numbers, we would be saying 10 multiplied by 2, which is 20. For this area here, you would say that the current is also 10, but then the resistance was only 1, and so that's only going to give us 10. So V1 is definitely going to be the larger voltage, and so that is the answer for this question. In which one of the following electrical machines is electrical energy converted into mechanical energy? So we know that a generator generates electricity. But how does it generate electricity? Only when you cause the armature to rotate. So a generator uses mechanical, and then it converts that into electrical. If we look at a motor, then that uses electrical, and it converts that to mechanical. And so this one can't be the answer because that's a generator. That's a generator. A dynamo is also some type of generator. So the only answer can be D, because we want it to be a motor, because we're going from electrical to mechanical, and that's what a motor does. Which one of the following combinations correctly links an emission spectrum and an absorption spectrum to the energy transitions of an electron in an atom? Alright, so what I'm going to quickly do is just draw a little an atom. So there's like the nucleus, for example, and then these are the energy levels going around. I'm just going to draw 2 like that. Now, we know that when and let's say this is energy level 1, and this is energy level 2. We know that when light is shone onto this atom, we know that the electron, let's say this is an electron over here, when it absorbs some of that light, it gains enough energy to be able to go up to an energy level. So we can say here, when an electron absorbs enough energy, it can go to a higher energy level. Okay, and then what happens is that when that little electron that we just spoke about now, when it jumps up to this energy level here, okay, then what happens is that after a small amount of time, it might decide to go back down again, because it doesn't feel very safe, because it's not a very stable environment, it's very high energy. So what happens is that this little electron might decide that it wants to go back down again. When it goes back down, it releases, or it emits or releases, it's the same word, it emits or releases energy. So we can say here, when an electron emits or releases energy, it can go to a lower energy level. Okay, so emission is associated with going to a lower energy level, and absorption is going to a higher energy level. So with absorption, we're going from a low to a high, so it could be that one or this one. So the answer is going to be D. I just see it here now, because here we're going from a low to a high, and that's the absorption, because you're absorbing energy, so you can go from a low to a high, and then when you give that energy away again, then you would drop back down from a high energy back down to a low energy. The first thing that I want to mention is that these are all the questions that we're going to be doing. So there's 5 of them, but I will be splitting them up over different pages in order to save space. So if I go forward there, we're going to do the first 3 questions on that page, and then we're going to do the last 2 on that page. But these are all of them that we will be doing. So let's begin. They tell us that we have a 20 kilogram block that is placed on a rough surface. Rough. So that means friction. At 30 degrees, a constant force F. Some people I've seen in the past, they see this word constant, and then they think, oh, constant velocity, constant. But no, guys, they're saying constant force. Okay, so that's actually nothing. You don't even have to worry about that word constant. They're not saying constant velocity or anything like that. When they say constant force, it's always a constant force. This force never changes, okay? And then it says that it's acting parallel to the surface, is applied to the block so that the block moves up the incline. Okay, now this is important. We are moving at a constant velocity. That is so important. So what that means is that the acceleration is 0. We must remember that. So the first question and then it says, a constant kinetic friction force of 18 newtons acts on the block. Okay, so that's quite nice. And then it says for the first question, state Newton's first law. There is the definition over there. It says that a body will remain in its state of rest or motion at constant velocity unless a non-zero resultant force acts on it. Number 2.2. Now, there is actually this thing that I've been noticing with a lot of learners. They have identified, and they are correct, that the Mach allocation for a free body diagram is a very nice way to see how many different forces we would need. So because this one is worth 4 marks, it typically means that there are going to be 4 different forces. But you must remember, on a slope we have gravity, right? Now, there are 2 different ways that you can do a free body diagram when you are on a slope. So pay careful attention quickly, guys. The first option is that you keep FG, okay? And then the second option is that you break FG into components. Both of them are correct. Okay, so if we keep Fg as it is, then what we're going to have here is we're going to have an applied force. Okay, so we're going to have an applied force. We'll say F. Then there is friction. They did tell us that. So if we know that the box is definitely moving up the incline. Be careful there. Sometimes this force is acting to the right, but the object can still be going downwards. Maybe the gravity parallel is larger than this force, or something like that. But they tell us that we are going up the incline. So friction would definitely act in the opposite direction like that. Then there's normal force. Now, I'm going to just say N, but if you say Fn, there's nothing wrong with that. On the memo, they actually allow for both. So there's your normal force. Now, over here, you could say W, all right? But what I'm going to say is Fg. But notice that I've kept it like that. I didn't break it up into parallel and perpendicular. So let's count how many forces there are. There's 1, 2, 3, 4. And that is where the 4 marks comes from over there. Now, if we break it up into components instead, then what we would get is there would still be a force. There would still be a friction force. There would still be a normal force. But now we would break it up into Fg perpendicular and Fg parallel. Now, some of you might say, hey, Kevin, but now there's 5 different forces. I agree with you. But when you look at the Mach allocation for a free body diagram, if you choose to use Fg parallel and Fg perpendicular, that only counts as 1, okay? So I hope that that makes sense. Okay, now me personally, I prefer to break it up into components. So I'm going to erase this part now. Because the reason I like to break it up into components is that it just allows me to easily see the different forces and the different factors that are contributing. Okay, so for 4 marks for the next question, calculate the magnitude. Magnitude is just the size of this force over here. So this is definitely just going to be a F net equals to MA kind of question. So the different forces, now all that I do, and I'm going to say up the slope is positive. Now all that I do is I look at my free body diagram and I look at all of those forces acting like that. So that means I'm going to have F minus friction minus FG parallel. Okay, those are the 3 forces that I had, and then I'm going to make that equal to MA. So now I can go and fill in F. That is what I'm trying to calculate. The friction force is 18 newtons. FG parallel, some of you forget, but that is mg sin theta, not cos. So that's going to be 20 times 9.8 times by the sin of 30. And then that's just going to be equal to the mass, which is 20, multiplied by the acceleration, which is 0. We said earlier that the acceleration is 0 because we are moving at a constant velocity. And so now we can just say F minus 18 minus, now I'm just going to type all of this, 98 equals to 0. And if we then have to go solve, we would find out that F is equal to 116 newtons. And you don't have to say up the slope or down the slope because they asked us for the magnitude. When they say magnitude, it only means the size. You don't necessarily have to also give the direction. Okay, so I'm just going to remind us that we've now worked out that this force was 116 newtons. It then tells us that the force F is removed. Okay, so the force F is going to be removed when the block reaches this point X over here. Okay, so before we even read further, think about what that would do to this object. The object will continue to move upwards for a little bit because it has a bit of momentum. But because we've removed that force applied, the object will begin to slow down. Okay, but it won't just stop and start moving in the opposite direction. It will still continue to go up the slope a little bit, but then it will begin to slow down. So it says that the block continues to move up the surface and then comes to rest at point Y. Okay, so it's going to stop over here, up here at point Y. So it says that assume that the kinetic friction force acting on the block remains 18 newtons like it was. Write down the net force acting on the block as it moves from X to Y. The answer is not 0. Okay, so let me quickly explain. So if we do our free body diagram, now that this force has been removed, so we can actually just take that force away. Just use some Tipex. Guys, I must share a funny story. So you see how I just changed the color of my pen to white so that I could erase that line. But the problem with that is I need to be able to see where my cursor is at any given moment in case I want to go choose a different pen color on my screen or a different eraser. So now when I change it to white, it takes me like at least 30 seconds to try figure out where the eraser is and everything on the screen because my cursor is white. I cannot see where it is, so I have to try just keep tapping until I eventually click on the right button. So yeah, random story, but that does happen, so it's quite funny. Okay, so we're going to quickly draw a free body diagram now, because now you can probably see, I'm not sure if it shows, but you can see that I've got a red cursor that's moving around, but when it's white, I'll quickly show you. Okay, so now I have a white cursor. See how awkward this is? Now you can't see anything. Maybe you couldn't even see the red one. I can't even remember if my cursor ever shows. But if it does, I mean, you'll see what I'm talking about. Okay, so we're going to do a new free body diagram. So everything stays the same, really. We still have friction. The object is still moving up the slope. We must remember that. It's not moving down the slope. There's no applied force. There is a normal force. There's still going to be gravity parallel. And there's still going to be Fg perpendicular. So it says write down the net force. So some of you might have said 0, but that's only if we were still moving at a constant velocity. And that was only earlier on when the applied force was still there. But that applied force is not there anymore, so we're not moving at a constant velocity anymore. Our object is actually going to slow down. So the net force is now going to be just these two. Okay, so just those two there. And they're both going to be negative because we're going upwards as positive. So we're going to say minus F minus Fg parallel. And so that's going to be minus 18 minus mg sin theta, which is 20 times 9.8 times sin of 30. And if we had to go fill that in, it's now going to be minus 116. Oh, I guess that does make sense. If the upwards forces, and I see that's why it's only for 2 marks, the upwards force was 116, so the downwards force was also 116, because we said that the object was moving at a constant velocity, so everything was balanced. Then if you take that other force away, then of course the only other forces that are still there would be these ones, and so it would just be negative 116. Now they are asking for the distance between points x and y, and that is for 4 marks. Right, so I'm going to take a grade 11 approach. If you are a grade 12 learner watching this right now, you could probably use your W net equals to delta EK kind of formula. That will work, but I'm just going to do a grade 11 approach, which grade 12 learners can also use, and that is just to use F net equals MA to find the acceleration. And then, and you can't say that the acceleration is 0 because we're not moving at a constant velocity anymore. And then we can combine that with this formula over here later on. So the F net is, and let's say upwards is positive. Okay, so the F net is minus 116. The mass of this object is 20. And so if we have to go work out the acceleration, we get minus 5.8. So let's just say that therefore, the acceleration is negative 5.8 meters per second to the minus 2. Now we can use that acceleration in this formula here. We know that the final velocity is 0 because they are going to, the block will come to rest. The initial velocity is 2 and the acceleration is minus 5.8, but we don't have the distance. So the final velocity will be 0. Let me actually write this over here. So the final velocity will be 0. The initial velocity is 2, see there? That's when, just before that other force was removed. The acceleration, please remember that there's a negative, and then the delta x. Okay, now you can solve this in multiple ways, but I'm going to take this over to the right-hand side. So we'll end up with 4 equals to 11.6 delta x. And so if you had to get delta x alone, you would say 4 over 11.6. And that should give us 0.34 meters. The first thing I want to mention is that these are not the only questions we're going to be doing. This question does carry on. So there's 3.1 and 3.2. 3.2 then carries on over here. And then lastly, we also have a 3.3. So let's begin. We have a hot air balloon that is moving upwards at a constant unknown speed. Okay, so it's moving at a constant speed, so that means its acceleration is 0. That's for the hot air balloon. Then it says that, is the hot air balloon in free fall? Choose from yes or no. Give a reason for the answer. An object is only under free fall if it is acting under the influence of gravity only. Now, if this hot air balloon was acting under the influence, if it was only being acted upon by gravity, then it would not remain at a constant speed. What would be happening is if it was going upwards, it would begin to slow down because of the gravity that is acting downwards. It would then reach a 0 velocity, and then it would begin to fall. That is what would happen if it was only gravity acting on that object. But they tell us that it's moving up at a constant speed. So these little, this fire over here that keeps the hot air balloon going, there's definitely some type of applied force over there. So is the object under free fall? No. And then we can say something like, gravity is not the only force acting on the hot air balloon. Gravity is not the only force acting on the hot air balloon. Okay. Then, okay, so that's our first question. 3.1, done. The next one, it says that when the balloon is 200 meters above the ground, a small stone is dropped from the balloon. Okay, so we're going to drop a little stone. Then it says another small stone, B, is going to be dropped. So dropped, okay, 5 seconds later from the balloon, while the balloon is still moving upwards at a constant velocity. Stone A hits the ground at a speed of 62.68 meters per second. Calculate the speed of the hot air balloon. Okay, now we need to be careful. Whenever we normally see the word dropped, that normally means that the initial velocity is 0. But that is only true when we are on a type of question where we are, for example, at the top of a building. And if they tell you that something is dropped when they're at the top of a building, then the initial velocity is 0. But when you are in a hot air balloon, or any one of these types of questions where you've got a pile of bricks on a crane, or a motor going upwards, or a hot air balloon going upwards, I want you to please remember the following. The initial velocity of the object that is dropped, okay, so that could be a stone, or a brick, or a camera, you know, they always like to use that camera one, or any type of object will always be the same as the velocity of the hot air balloon, or sometimes it's a crane, or anything like that. Okay, so what we can say is that the initial velocity of the object that is dropped will always be the same as the velocity of the object that it is dropped from. So the velocity of, for example, the hot air balloon, or the crane, or anything like that. Okay, they like to ask this type of question, and you need to remember that. Many people think, oh, but Kevin, if you drop that thing, won't the velocity be 0? It's not true, guys. What happens is that as soon as you drop that object is actually going to go up a little bit. It's going to slow down, and then it's going to start coming down. Yes, if you were in the hot air balloon, you wouldn't see that, but it's all relative. Okay, it's relative motion. So if you were standing somewhere over here on the ground and you watched the person dropping it, that person would maybe see the object going up a little bit. But if you are the person who's standing in the hot air balloon, you won't see that the object also goes up a little bit. Okay, but you must remember that it does. Okay, so when they ask us for the speed of the hot air balloon, what we can remember is that the velocity of the hot air balloon is the same as the initial velocity of the stone. Remember, because that's what was dropped. So we can use the stone now, and let's see what we have. We know the final velocity of the stone. We are trying to find its initial velocity, so that's what we're actually looking for. We know that the acceleration is 9.8, because that's what happens when an object is falling under free fall. Yeah, but Kevin, we said it's not free fall. Guys, the hot air balloon is not under free fall, but the stone is under free fall. As soon as you drop that stone, the only forces acting on it would be gravity. And then we also know the displacement, which will just be 200. Some of you might say, yeah, but Kevin, it goes up and then it comes down, so isn't the distance a little bit more? Guys, this is not distance, this is displacement. So if you look at how far it falls from there to there, that's only going to be 200. Yes, it does go up a little bit, but then it also comes down, so that cancels out. Displacement is how far does it fall from the beginning to the end, and you must look at it in a straight line. Okay, and so we could possibly go and use, but we don't have anything relating to time, so we could use this formula from our formula sheet, because this is the only equation of motion that doesn't use time, and we need to choose a direction as positive. It doesn't really matter, but I'll just choose downwards as positive. Okay, so the velocity when it hit the final velocity is 62.68 squared. The initial velocity we have no idea, but it's squared. plus 2. Now gravity or acceleration is 9.8, and it is acting downwards, so we can say 9.8 is positive. And then the displacement. Sometimes the displacement is negative, so let's see. We're choosing downwards as positive, and let's see, the object starts over here, and it ends up over here. So it is ending up below the starting position. So that means, and we're choosing downwards as positive, so that means the displacement is a positive value. Because we're choosing downwards as positive, and the object is ending below the starting position. So that is a positive displacement. And so now we just need to go and calculate for initial velocity. So on the left-hand side here, after we square that, you're going to get 3928, don't round off, 0.7824 equals to the initial velocity squared plus 3,920. Take that over to the other side, and you end up with 8.7824. Then remember to square root, and so we should get 2.96 meters per second. And they just said speed, so you don't need to give a direction, because speed is like a scalar, it doesn't have direction. So that is the original velocity of the stone, but that also means it's the original velocity of the hot air balloon, because we said that the object that you drop and the object that you are dropping it from, like the crane or the hot air balloon, those two things have the same velocity at the beginning. Okay, so that answer is 2.96 meters per second. Okay, so we must just remember that for future questions, that hot air balloon originally began moving at that's the velocity that the hot air balloon is moving at, and that's also the original velocity of the stone. Next question for 3 marks. How long does it take for the stone A to touch the ground or to strike the ground? So this one we could probably just use this formula here. Yeah, you could use others. You could possibly also use this one, delta T. Yep, that would also work. So I'm going to choose downwards as positive again for the stone. We know that the final velocity of the stone is 62.68. We know that its original velocity is the 2.96, what we said. But we've got to be careful. Minus 2.96. Why? Because we're choosing downwards as positive, but that stone originally went upwards for a small amount of time. Okay? The gravity will be positive 9.8 because we chose downwards as positive, and gravity is downwards. And then the total time is actually what we're trying to calculate here. So I'm going to take that 2.96 over to the other side. And so that's going to give me 65.64, and then on the other side I'm still going to have that. And then if we have to go work out the time, we should get 6.70 if we round off. 6.70 seconds. Okay, so let's just remember we're moving on to the last part now. Oh no, we still have a few more questions actually. So we must remember that the original velocity of that stone was 2.96. We must remember that the total time to hit the ground, I don't know if we're going to need this stuff, but let's just see, 6.70 seconds. Okay, so it says when the balloon, okay, we already saw that. Stone A strikes the ground. Okay, so we did all of that. Then it says calculate, they love to ask this kind of question. Calculate the distance between the hot air balloon and, there's also a stone B. This is interesting. Calculate the distance between the hot air balloon and stone B at the instant when stone A strikes the ground. Okay, so this isn't too bad. What we must understand was that stone A went upwards and then it hit the ground in 6.7 seconds. Okay, so that's how long that took. What we must remember was that stone B was only dropped 5 seconds after stone A. So how long has stone B been in the air for? How long has B been in the air for? Well, we know that it was stone A was in the air for 6.7 seconds, but stone B was thrown 5 seconds later, so stone B has only been in the air for 1.70 seconds. Okay, so that is how long stone B has been in the air for, 1.7 seconds. So what we can now do is we can try to work out how far would stone B have gotten downwards in 1.7 seconds. So let's quickly do that. So that's what we're going to see. So we can use this formula to see how far would stone B go downwards in 1.7 seconds. So let's choose downwards as positive again. So we're trying to see how far it went down. We know that stone B would also have an initial velocity of 2.96 because it's coming from the same hot air balloon. I've put it as a negative because it would originally go up, but we chose downwards as positive. We know that stone B will be in the air for 1.7 seconds. We know that gravity is 9.8, and we know that the time again is 1.7 seconds. And so if we go work out this, I'm not going to round off because it's not my final answer, so I'm going to say 9.129 meters. Now that's not the answer. That is how far B has gone down. But at the same time that B was going down, the hot air balloon was going up. But what's nice about the hot air balloon, we can use the same formula for the hot air balloon actually. Let's keep downwards as positive. I know that you learners like to keep one direction as positive. Sometimes I choose both, but then some people comment and they're like, so I don't understand. So let me keep it downwards as positive. What we must remember is that the hot air balloon does not have an acceleration. But Kevin, this is vertical projectile motion. Yes, but the hot air balloon is not in free fall. Remember, that was the first question they asked us in this question was, is the hot air balloon in free fall? And it's not, because it's moving at a constant speed. Okay, so it doesn't have an acceleration. So we can just say that its distance or displacement that it's going to cover will be its initial velocity, which is negative 2.96, because I chose downwards as positive, but the hot air balloon is going down, and the time is also 1.7. And if we had to work that out, we get negative 5.032 meters. But because we chose downwards as positive, we can then say, therefore, the hot air balloon is 5.032 meters that it has gone up. Okay, so now the distance between the hot air balloon and B will simply be equal to the 9.129 meters plus the 5.032, because the hot air balloon is going up and the stone went down, and so if we add that together, we should get 14.16 meters. And here's the last question for this whole question. So they want us to, on the same set of axes, draw a position time graph for both the hot air balloon and stone A. So, okay, so let's draw our y-axis, which is the position. So we can just say here, position in meters, and this would be our time, measured in seconds. And they said use the ground as the reference. Okay, so this is the ground. So where do we start? We start at 200 meters. Okay, let's do the hot air balloon first. The hot air balloon starts at 200 meters, and it will just continue to move upwards like this at a constant rate. Okay, it's not going to be a curve that does something like that, because that would mean that the hot air balloon is getting faster and faster and faster. So this will be the balloon. They've asked us to call that balloon. Now let's look at what would happen to the stone. The stone would first go up a little bit. Okay, so let's show that it goes up. But we can't let it go above this line, because that means that the stone overtakes the hot air balloon. Imagine how weird that would look if the stone overtakes. So it doesn't overtake. So its line goes sort of there, and then it would turn, and then it would hit the ground like that. Okay, and so it went up a little bit, and then it would hit the ground. Make sure that these two time intervals are in line with each other, so that would be at 6.7 seconds. And that's all that you can really draw. We must label this graph as A. And so that's it for that question. These are all the questions that we are going to be doing in this question, but I'm going to split them up over different pages just so we have a bit more space. So here's 4.1, 4.2, 4.3, but I'm going to have 4.1 on that slide, 4.2 on that slide, and then 4.3 over there. So let's get started. So here we have a ball X of mass. Okay, now actually before I even say that, guys, what you want to get into the habit of is, so here we can see that we're going to have two objects, right, that are probably going to be crashing into each other, or they're going to be colliding. As soon as you see that, where you've got two objects that are crashing into each other or moving apart or anything like that with two objects, the objects are not connected with a rope. If they were, then we would probably want to use Newton's laws, F net equals ma. But here we've got two objects that are going to crash into each other, or they're going to bounce apart, or something like that. Then I instantly want you guys to always just have in the back of your mind the conservation of linear momentum. Okay, so the formula we're probably going to have to use just now is going to be that one that goes, the one that's like m1 v1 initial plus m2 v2 initial equals to m1 v1 final plus m2 v2 final. You know that one, right? I know I'm not writing it very neatly there, but I'm just giving you a quick little note. That is what my mind does when I see a question like this, okay? I instantly think, it's probably going to be one of those. Okay, maybe it won't be. But let's see. I don't go through these questions before I record them. This is actually the first time I'm doing this question right now. Some students probably think that I go through the question, I do the question, I check the memo. But I actually don't at all. This is literally, I haven't even read what this stuff says. It's more fun for me to just do it naturally and without making little notes and stuff like that. That would be so damn boring. And yeah, so that's why, I'm just doing it raw, like right now with you guys. So it's probably going to be something like that, but let's go on. So it says that we have a ball of mass 10 kilograms. Okay, so this is a 10 kilogram ball over here, and it's moving to the eastward side or eastwards with a velocity of 2 meters per second. It collides elastically. Okay, that's important because remember that two objects can collide, but you can get different types of collisions. You can get elastic collisions and you can get inelastic collisions. Okay, so it collides with a ball Y of mass 2 kilograms. Okay, so this ball is 2 kilograms, which was moving with an unknown velocity. Okay, so we don't know what this ball was doing. We don't know if it was moving to the left or if it was moving to the right. Doesn't really matter, but it was moving. Okay, then it says immediately after the collision, ball X comes to a rest. Okay, so it stops immediately, so it's at 0 meters per second, and ball Y is going to move eastwards. Okay, so ball Y is going to move eastwards. They're showing us that with a kinetic energy of 36 joules. Okay, so the first question for 2 marks, explain the meaning of the term elastic collision. Okay, so let me just give you guys a quick little summary. As we said, we get two types of collisions. The first one that we get is called an elastic collision. And in this one, the kinetic energy, the total kinetic energy, so let's go the sum, that's a symbol for sum, like sigma. So the sum of all the kinetic energy before the crash, so I'll say initial, is exactly the same as the sum of all the kinetic energy, kinetic, so it's energy, kinetic, final. So the total kinetic energy before the crash or the collision is the same as the total kinetic energy after the collision. Okay, and then we get a inelastic collision, and this is just the opposite. This is where the sum of all the kinetic energy initially is not equal to the sum of all the kinetic energy final. So those are the two main collisions we get. And so there is the definition of an elastic collision. It is a collision in which both the total momentum and total kinetic energy are conserved. So here I was only talking about the kinetic energy. I didn't talk about the total momentum because in both of these types of collisions, the momentum is always conserved. Okay, so in grade 12 questions like this, where you've got objects colliding, the total momentum is always conserved. And that's what I was trying to show over here. Whereas the kinetic energy, that doesn't always have to be conserved. If it is, we call it elastic. If it isn't, then we call it inelastic. But the total momentum, that is always going to be conserved. Okay, that's the conservation of linear momentum that I referred to earlier on. Here is the next part. So it says calculate the velocity of y. So what they mean is, what was this one's original velocity? Okay, so we know that it's going to be one of these questions where we can say that the sum, that means sum, right? It's not an E. Some students always say, is that an E? No, it's not. That means sum, like we do in sigma notation in maths. So we're saying that the sum of all of the momentum is a P, initial, I was going to say initial, I don't know how that even makes sense, initial, which means before the crash, will always be equal to the sum of all of the momentum after the crash. That is what we are saying, okay? Then choose a direction. So let's say that to the right is positive. You can say to the left if you want, it's not a problem. Right, so we can say that we've got the mass of object X multiplied by the velocity of object X, and then I'm going to put an I. That I means initial, before the crash. Then I'm going to say plus, because we're looking at the sum. That's how this formula works. Then we're going to do the object Y. So the mass of Y times the velocity of Y initially equals. Now we're going to do the same thing on the side, but this time around it's going to be the F, meaning final, after the crash. And then we're going to do the other object, Y, final. There we go. Now, okay, so now we would just go fill everything in. So the mass of object X was 10 kilograms, or is 10 kilograms. Its original velocity is 2, so we can just say times 2 plus the mass of object Y is a 2 kilogram object, but we don't know what its original velocity is, and we don't need to know the direction. It'll all sort itself out, and it'll tell us that just now. And then for the next part, we now need to look at the mass of object X, which is still going to be 10 kilograms, and its final velocity was a 0. So we'll put a 0 over there, plus, now we're going to do, okay, now this is interesting, but it's not difficult. They tell us that its kinetic energy is 36. Now we know that the formula, on our formula sheet for kinetic energy, not the change in the kinetic energy, just kinetic energy, is a half mv squared. So we can say 36 equals to a half. Now the mass of that object was 2 kilograms. And then we can say v squared. And if you had to go and work this out, you would end up with a half times 2, which is just 1. To get v alone, you would square root, and you would get plus minus 6. But we'll just take it as positive 6, because we know that it's going to the right-hand side. And they did tell us that it moves eastwards. Okay, so we'll just keep it as 6. So we can say here then, well, let's say v equals to 6 meters per second. And we can actually say to the, well, let's say to the east, because that's what they're using here. So we can say east. Okay, so now we can just go fill this in over here as 2. And its velocity is 6. Right, and then our next part would be to try calculate the velocity of y. Now, I'm just going to go and calculate it along, because that part's fairly straightforward for you guys. Right, now you should get an answer of -4. Don't worry about the negative. What it means is that the velocity of y, which was this part here, it was actually originally moving to the left. So we can say 4 meters per second. Don't say left, say west rather, because that's what they're using. West. Okay. And then question 4.3. Okay, well, let's just first remember that this one was moving 4 meters per second west, and we know that this is actually 6 meters per second. I don't know if we'll need that, but just in case. Here it says that the balls were in contact for 0.1 second. Okay, so that's a time and then force. Right. They like to do this, guys. So whenever they have two objects, then we like to think of, like I said just now, we like to think of the conservation of momentum, right? But when they start in the same question talking about time and force, then we want to use this formula here. And this formula is on your formula sheet, okay? So whenever they have a question like this where it's also two objects, not always two objects, but yeah, whenever it's one of these, you're going to use this formula here because it talks about momentums, it's got the net force, which we're talking about, and it's also got time. Okay, and with practice, guys, you begin to know exactly which formula needs to be used where. If you're not at that point yet, it just needs more practice, okay? If your exam is tomorrow, hey, I hope that tomorrow you'll just remember in this type of question that you'll use that formula. Sometimes you don't need to do so many examples to know what to do, okay? So let's quickly go and do this. So they say, calculate the magnitude of the force that bore X. Now, here's the important part. Bore X exerts on bore Y. So who are we trying to measure the force of? Or which object is experiencing the force? Is it object X or is it object Y? Well, it says that bore X exerts on bore Y. So we want to know what is bore Y experiencing. So we're going to use this formula only on bore Y. You're not going to do it on bore X. Okay? So let's go write down the formula. Once again, we need to choose a direction. It doesn't really matter. Let's say right is positive. And so we're going to go calculate the force. We can say F net. Now, delta P, if you look on your formula sheet, they also show you that, I'll write it over here for you. Delta P is just MV final minus MV initial. So let's expand it into that. MV, so I go do it the wrong way. MV final minus MV initial over delta time. Okay, so F net. Okay, now we look at the mass of bore Y. We want to use bore Y, which was 2 kilograms. Bore Y's final velocity was 6 meters per second to the right, so we can just do it like that. Its original velocity was 4, but to the left, so you must put it as a negative, because we said right is positive, but that one's going left. These are the little areas where students make mistakes, and then the time is 0.1. Go ahead, type this all in, and we end up with 200 newtons, so we can say, therefore, 200 newtons to the right, because we chose right as positive, and we got a positive answer. The first thing I want to mention is that these are all the questions that we're going to do, but I will be splitting the questions up onto different pages just so that we have more space and it's easier to work with. So these are all the 4 questions. We'll do 5.1 and 5.2 on this slide, 5.3 over here, and then 5.4 over here. Let's get started. So we have a 2 kilogram box that is released from rest. Okay, so that's important. When they say from rest, it means that its original velocity or initial velocity is 0. 5 meters above the ground. Okay, so it started over there. It slides down a smooth, aka frictionless, track PQ. State the principle of conservation of mechanical energy in words. And so there I've written it down that the total mechanical energy of an isolated system remains constant. So what does that actually mean though? So let me give you a quick summary of the way it works, like mechanical energy and all of that. So let's say we have an object up here. Let's say, for example, you've got an object up there. And let's say that that object is not moving. So then what type of energy does it have? Well, the only 2 types of energy that we consider in grade 12 is potential energy and kinetic energy. Potential energy is energy because of height. Okay, and then kinetic energy is because of the speed or the velocity. So when the object is at P, what type of energy does it have? Well, if it's not moving, then it's going to have potential energy. Potential. Over here, the object is moving, so it's definitely got kinetic energy. And it also has some height above the ground, so it's also going to have potential energy. When it reaches the ground over here, it has no height, but it will have a bit of velocity, it will have some speed, so it will only have kinetic. Now, if you add these 2 together for an object, that is called mechanical energy. Mechanical energy is the potential energy plus the kinetic energy. That is what mechanical energy is. And if there is no external forces, like if there's, if there is no friction, applied forces, or tension forces, if there's none of those forces, then what we can say is that the mechanical energy is always going to be conserved. what that means is that the mechanical energy will remain constant. So if you had to go add up all of this energy over here, that would be the mechanical energy. If you had to go add all of this up, that would be the mechanical energy. And if you had to go add up this energy, that would also be its mechanical energy. At each of those places, the mechanical energy will be the exact same amount. All that happens is the potential energy and the kinetic energy, some of them become less, some of them become more. But if you had to add up the total mechanical energy remains constant. Okay, so in 5.2 it says, use the principle of conservation of mechanical energy to calculate the speed of the box when it reaches point Q. I just want to quickly explain one more thing. Maybe at the top here, the potential energy is 100. Then I'll show you. That's just an example, guys. That's not the answer. That's just an example. So maybe the potential energy is 100. Then what would happen is that at this point over here, maybe the potential energy is now 60. Then what would happen is that the kinetic energy would then be 40. And then at the bottom here, the kinetic energy would be 100. So that if you had to see the total mechanical energy at every single point, it will always be 100. See that? 40 plus 60 is 100, and then at the bottom there's only kinetic energy, so the mechanical energy will just be 100. So the mechanical energy remains the same, but the potential and the kinetic doesn't have to be the same. At the top here, the kinetic would actually be 0, and at the bottom here, the potential would be 0. So if you had to go add them up, you're always just going to get 100 joules for the mechanical energy. Now, okay. Those were just some example numbers, okay? Now, some students, well, if you've watched any of my videos on these types of questions, you would know that on a curved surface, there is only one formula that I ever use, and that is this one over here, this one here, okay? Because some students, they're like, yeah, but so mustn't we use the mechanical energy formula? But what I've said so many times in previous videos is that WNC is the work due to non-conservative forces, and that is things like friction, applied forces, and tension. But if you don't have any of those, which we don't have any of those from P to Q, the only forces from P to Q is gravity, but that is not a non-conservative force. So what you then do is you take this formula and you just make the WNC equal to 0. So let's actually do that over here. You just make that a 0, and then you're stuck with delta EK plus delta EP. Now, this is the mechanical energy formula. If you wanted to, you don't have to use this formula that I'm using. Then you could say something like the mechanical energy at P is equal to the mechanical energy, so that's not a, that's an E, the mechanical energy at Q. And then in this one's place, you would fill in the mechanical energy at P, which is the potential energy at point P, potential energy at point P, plus the kinetic energy at point P, and then that would be equal to the potential energy at point Q plus the kinetic energy at point Q. You can do that, but this formula is exactly the same thing actually. So on curved surfaces, I always use this formula, and if there is no friction or applied forces or tension, then I just make it 0, and then it is actually the mechanical energy formula. Some of you might be looking at this and you're like, yeah, but Kevin, these two things are not the same. And I will say, you are wrong. They are the same. I'll show you. If I want to look at the change in the kinetic energy, it would be the kinetic energy at Q minus the kinetic energy at P. It's almost like the final minus the initial. And then for the potential energy, I would say the potential energy at point Q minus the potential energy at point P. Then if I had to take all the negatives over to the left-hand side, then what I end up with is the kinetic energy at point P plus the potential energy at point P. So I just took the two negatives over to the left-hand side, and then on the right-hand side, I would still be left with kinetic energy at point Q plus potential energy at point Q. And bam, I've got the same formula that you guys are using. So I like to keep my life super simple, and I only use that formula on a curve. If there's no friction, applied forces, or tension, then I just make that a 0, and then it does the correct thing anyways. Okay, so this is like an awesome formula because it does everything I need it to do. I don't have to remember the mechanical energy formula and the WNC formula. I just use the one. Okay. All right, and then, okay, so let's quickly actually go do this now. So it's going to be the kinetic energy at point Q minus the kinetic energy at point P plus the potential energy at point Q minus the potential energy at point P. And then I'm just going to go find the zeros. So I know that at point Q, the potential energy is 0. So this part here is actually just going to be 0. And then over here, the kinetic energy would be 0. So the kinetic energy of point P would be a 0. So my formula is now like this. Kinetic energy of point Q minus the potential energy of point P. That is what my formula now comes down to. Now I need to just go fill in kinetic energy and potential energy, both of which are on the formula sheet. Okay, that's meant to be a P over there. I think I blocked that a bit. So there's your potential energy formula, and there's your kinetic energy formula. So I can just go 0 is equal to kinetic energy. Okay, so the mass of this object was a 2 kilogram object. Its velocity at point Q is what we're trying to find. So we can just say velocity at point Q squared. Please remember the squared. A lot of students forget that. Minus, now the potential energy at point P is going to be 2 times 9.8 times its height was 5 meters. And there we go. So what we'll end up getting now is 0 is equal to VQ squared, because these two just multiply to become a 1, minus 98. Take the 98 over and square root, and so your velocity at point Q is 9.90. I've done so many questions where the final velocity at the bottom is 9.90. 9.90 meters per second. Okay, you don't have to give any directions because they just asked for the speed. So just remember that, 9.90. Right, so we must remember now that when the box gets to the bottom here, it's traveling at 9.90 meters per second. Okay, so the next question says, the box passes point Q and then moves 10 meters on a rough horizontal surface before striking a barrier, point R, at 4 meters per second. Okay, I just want to talk about this a little bit. Here it was traveling at 9.9, and then here it's traveling at 4 meters per second. So obviously it does slow down because it's going over this rough surface. Some learners think if the box is here and they do a free body diagram, they think that there's some type of applied force, but there's no applied force. But then students are like, yeah, but Kevin, how's the box moving then? It's because it picked up a lot of momentum when it was coming down this slope, guys. But it's got no applied forces over here. There's no applied force. The only force acting on the box here would be friction, and that's why the box is slowing down. See that? And of course, there's still like normal force, gravity, but those are the only forces. There is no applied force. Please remember that. I know it's moving, but that's just because it had momentum that it picked up from that slope. And this is why the object is slowing down, because there is only friction. Okay, so it says the box, we read that. Use energy principles. Okay, when they say energy principles, if you've watched some of my lessons on this, you would know that there are, because we're moving, have a look here, guys, we're moving on a straight, or let me first say, when we're on a curve, then what formula do we like to use? We like to use WNC. I really hope this is becoming a clear picture for you guys after watching a lot of my lessons on this. And then when we're on a straight line, oh my goodness, we have so many options. We could go old school. We could go grade 11 if we wanted to. F net equals MA. Combine that one with VF squared equals to V initial squared plus 2A delta X. Those two work nicely together. That's one way. That's the grade 11 approach. We're not allowed to use that one in this question because they only want us to use energy principles. So your energy principles could either be W net equals to delta EK, that'll work, or you could even use WNC again. As long as you're on a straight line, all three of these can work. When you are on a curve surface, then I typically recommend you just stick to that one. You can use another one for there, but it gets weird. Okay, so we're not going to use this one. although it will give us the right answer, they did ask us to please use energy. So energy is these ones with the W, because W means work, which is energy. Okay, so it says use energy principles to calculate the magnitude of the average friction force acting on the box as it moves from Q to R. All right, so we can choose any one of these that you like. It really does not matter. I'm gonna go with this one. Why? Just because we haven't used it yet in this question. So let's go use that one. But if you wanted to use WNC, absolutely fine. Okay, so I'm going to use WNet equals to delta EK. Now, what I want to do is, okay, we've got our free body diagram. So the only forces that are acting on this object in this horizontal direction is friction. Okay, so remember that W is a type of work. So what is the formula for work? Well, here it is. This is the general formula for work. So that's what I will put in over here. But the only forces that we have is friction. So we'll just use the W because of friction equals to change in EK, which is always going to be a half mv final minus a half mv initial. So maybe we could actually just say at point R, that's your final position, and then at point Q, which is your original position. We're not going to say P. That's not what we're only looking from Q to R right now. Okay, now here we need to go expand this into Fx cos theta. So we're going to say the force due to friction multiplied by the distance, which we know is 10 meters, but I'll fill that in just now, and then cos theta. Okay, and then let's just go fill all this in, minus a half mv squared at point Q. Okay, now we can go fill everything in. So F we don't know, that's what we're trying to calculate. The distance is 10. Now we're going to say cos 180. Let me explain. Remember that when you use this formula, what is theta? Theta is the angle between your direction of motion and the force. So we're busy going this way, but the force of friction is that way. So that is a complete 180 degree angle. Okay, now we're going to go half. Now what was the mass? 2 kilograms. What's the final velocity? It's not 0, it's 4. Remember? 4. Minus a half times the mass. Now what was the original velocity at point Q? It was 9.9. 9.9, and there we go. Okay, so now we're going to end up with, on the left hand side, you're going to end up with negative 10F, because this is a negative 1. By the way, for this force here, you're never going to put that as a negative. Even though it's acting in the opposite direction, you don't put the force as a negative when you are using the work formula. You would only use the force as a negative if you were using like a grade 11 F net equals MA kind of approach. Okay. And so this cos 180 is the thing that makes it a negative. All right. And then on the right-hand side, I'm just going to go type this all in. And that gives us negative 82.01. And if we had to go and work out the friction force, we're going to end up with 8.20 newtons. And we don't have to give a direction because they just said magnitude. Okay, so let's just summarize what we have so long before we move on to this last part. So we know that the object reached this part at 9.9 meters per second. We know that the friction force here was, what did we say, 8.2 newtons. And we know that it reached this point at 4 meters per second. I don't know if we're going to need any of that, but hey, at least we've got it now. Okay, so it says that the barrier exerts an impulse. Okay, so impulse. The barrier exerts an impulse on the block to the left. Calculate the change in kinetic energy of the box after striking the barrier. Okay, calculate the change in the kinetic energy of the box after striking the barrier. Okay. So I think what we can do here is we can definitely go grab our impulse formula, which you can find from here. Okay, so impulse is, well, let's actually not use that one. These are all from the formula sheets, by the way. We can take this one. And then to get the impulse, you must get the F net multiplied with the time. That is impulse. Okay, so this over here is impulse. So what I think, and then we're going to choose a direction as positive. So I'm going to choose right as positive. Now they tell us that the impulse exerted on the box was 14 to the left. So I'm going to replace this part with 14, but it's to the left, so I'm going to actually replace it with negative 14, because remember, this is the impulse. That part there is the impulse. And then for delta P, remember that delta P is also given on your formula sheet as this over here. So what I'll do is I'll just go expand that into mvf minus mvi. But now remember, we're not talking about Q and R anymore. Now we are only talking about this area right here. So we know that it's going to hit the box at 4 meters per second, but then we need to, so we don't know what velocity it's going to bounce backwards at. You know, it's going to bounce backwards as well. It's obviously going to be a little bit less because it's going to slow down a bit. So maybe it's going to bounce backwards at 3, but we don't know. So what we do know though is that it's going to, let's just make this neat. It's going to hit this box at 4 meters per second, or this barrier, and then it's going to bounce back, but we don't know what that is. So what we can say is minus 14 is equal to, okay, so now the mass is 2 kilograms. We don't know what the final velocity is, and we don't need to choose its direction. Any unknowns, you just leave it like that. And then the mass is 2, and then the original velocity before it hit the barrier was 4. And it was to the right, so we can leave that as a positive. So now we can calculate the final velocity that this box after it hits the barrier. So that's going to end up becoming minus 14 plus 8, because this is 8, but I'm taking it over to the other side. Oh, there's a little 2 there. So we're going to end up with 2vf is equal to minus 6. And so the final velocity is minus 3, and so therefore the final velocity was 3 meters per second to the left. I actually predicted that one correctly just now. 3 meters per second going to the left. So now we can calculate the change in the kinetic energy of the box when it strikes the barrier, because we know that change in kinetic energy would just be the kinetic energy final minus the kinetic energy initial. Okay, kinetic energy doesn't really need a direction because it's, well, let's choose one anyway, so we can say to the right is positive, for example. Okay, so what we can then calculate, you'll see why it doesn't really affect the answer, but let's just do it. So we can say the final kinetic energy would be a half times the mass, because remember kinetic energy is a half mv squared. So we can say half times the mass. The final velocity is 3, but it's to the right, to the left, so we'll do that. Okay, and then we say minus a half 2 times 4 squared. And if we had to go work this out, we'll end up with negative 7 joules. Now we're not going to say 7 to the left or 7 to the right. Kinetic energy is a scalar and it's not a vector. So you don't say direction for kinetic energy. You won't say 7 joules left or 7 joules right. You'll just leave it as negative 7. Let me write that a bit better. It looks like an arrow. Minus 7. The first thing I want to mention is that I know there's a lot of words on the screen over here, but these are all the questions that are part of this question, but I will be splitting them up over the next few pages just to make more space for us, okay? So this is going to be 6.1, then we'll be doing 6.2 and 6.3, and then we'll have 6.4 over there. So here's 6.1. It says that the siren of a stationary, okay, so that means it's an ambulance that sells like pencils and calculators and stuff, because it's a stationary ambulance. Guys, that was a stupid joke. Stationary means that it's not moving, okay? So it's not like a Walton's ambulance or something. Okay, thumbs up if that made you laugh. So let's go. Let's say that the velocity is 0. That's what stationary means. It means it's not moving, okay? So the siren of a stationary ambulance emits sound waves at a constant frequency of 680. Okay, so this little siren can emit sound at 680 hertz. That's its frequency. A man is standing with a detector. So here's the little detector. It looks more like a, what the hell is that? Like a TV or something? Jesus, question must be from like 1631. So a man is standing with a detector that records the wavelength of the sound emitted by the siren. The speed of the sound in air is 340. Calculate the wavelength. Okay, guys, so this is obviously a Doppler effect question. Now, the Doppler effect, we use two main formulas. One of them is the one that we see on our formula sheet, which goes like this. All right, that's the one formula, but then we mustn't forget about the V equals to F times lambda, where F is frequency, lambda, is wavelength, and then this is the velocity. And okay, so it says, and when we're using this formula here, or let's first see something, calculate the wavelength of the sound. Okay, so we're talking about, when we use this formula, we're going to use the sound. We're not talking about the ambulance, so you're not going to put a 0 there. We're talking about the sound. How fast does the sound move? Well, they tell us that the sound in air is 340, so we can say 340. The wavelength of that sound is, we've been told, is 680, and now we're trying to calculate wavelength. Now 340 over 680, that would give us 0.5 meters. So that is the wavelength of that sound. So moving on to the next part now, they tell us that the ambulance now starts to move. Okay, so remember the ambulance wasn't moving, and now it's deciding to start moving at a constant speed along the road towards the man. Okay, so it could be reversing. It could have been reversing, but they've made it clear that the ambulance is going to go forwards towards the man. The detector now records the wavelength of the sound. Now, be careful here. I nearly got caught out with this one, which differs from the previous reading by 0.05. They're not saying that the new reading is 0.05. They're saying that the reading differs by 0.05, okay? So the previous reading of wavelength, if you can remember, was 0.5 meters. So this little detector now is maybe reading 0.55 or 0.45. We'll talk about that just now, but it's definitely 0.05 higher or lower than it was before, because they said that it differs from the previous reading. The first question says, state the Doppler effect. And so there's the definition. It is the apparent change in observed frequency as a result of the relative motion between a source and an observer. Next part. How would each of the following have changed when the ambulance approached the detector compared to when the ambulance was stationary? Okay. So remember, in the first part of this question, the ambulance was not moving, okay? And when it was not moving, it was giving off a wavelength of 0.5. So that means that the distance between two parts that are in phase was 0.5 meters. Now, you got to think to yourself, what would happen to these waves when the ambulance begins to drive in that direction? Well, what happens is that ambulance will begin to squash or compress those waves. So those waves will actually become a little bit shorter. Okay, how much shorter? Well, they told us 0.05. It will be different. It'll differ from the previous one by 0.05. So it definitely won't be this wavelength. It'll be this one over here. That wavelength will become shorter because the ambulance is going to compress the waves. So it says here, what will happen to the distance between the wave fronts? That will definitely decrease. What will happen to the frequency? Okay, well, let's see what frequency is. So let's say this is the original 0.5 meters, and let's say that's the original. Now, if we make the wavelengths shorter, look at what happens to the frequency. What is frequency? Frequency is the number of waves per second. So in the red one, which is the 0.45 meter wavelength, as we make the wavelength shorter, what do we do to the frequency? Well, we definitely have a much larger amount of waves, so the frequency, which is the number of waves per second, will increase. And the last part of this question asks us to calculate the speed of the ambulance. Okay, now remember the ambulance is moving. It is moving, so it's not standing still anymore. So we must remember that the frequency given off by this part here is 680, and the wavelength we now have a 0.45. That's the sound, and that's the only information we have. We do know that this dude is not moving. Okay, and we don't know what the velocity of this ambulance is. So we know that we're definitely going to have to use our Doppler effect formula, which looks like this. But now the question is whether we use a plus or a minus or a minus or a plus. Now remember, the way that it works is that when the two objects move towards each other, then we always use a plus at the top and a minus at the bottom. And then if the objects move away from each other, then we use a minus at the top and a plus at the bottom. So because these two objects, although the person is not moving, they are still getting closer together. So we will use a plus at the top and a minus at the bottom. So a plus at the top and a minus at the bottom. Now let's just fill in some information. The FL is the frequency that the detector will hear, or the man and his detector. Okay, so that will be the frequency of the detector because that's the listener. V is just a constant of 340, which they gave us. VL is the velocity of the listener, which is the detector, which is not moving, so that's 0. VS is what we're trying to find. It's the velocity of the ambulance, which is the source of the sound. And then what else? FS, oh, that's the frequency of that the ambulance siren is making. And so that would be the 680. Okay, but that's not what the detector will hear because the objects are moving. So it's the frequency of the alarm, which is that 680 value. Now, okay, now we need to, the unknown is this one. This is the one that we need to get, but we also don't know what this is. So we quickly need to work that out because now we have the wavelength of the sound. So we can just use this formula. Whoopsie. We can just use this formula again because we know that the sound is traveling at 340. The frequency we don't know, but the new wavelength is 0.45. So if we had to work out the new frequency, it should be more than 680 because the ambulance is coming towards the person. 755,5. I'm not going to round this off because it's not the final answer. So 755,5555555. Okay. Right, so now we can go fill everything into our formula. So we can say 755,555, and that just keeps going. That's the listener, and then that's equal to 340 plus 0, because the listener is not moving, over 340 minus Vs, which is what we're trying to calculate, and then the frequency of the source is 680. Now, some of you are probably having a heart attack right now, like, how are we going to solve this? Well, there's multiple ways. What I'm going to do is I'm going to multiply this to the left, so we would end up with this. And then on the right-hand side, you're just going to have 340, because 340 plus 0 is just 340, right? And then we still have the 680 over there. Now, I know some of you probably want to multiply this into the bracket, and there's nothing wrong with that, but I'm rather just going to divide this on the on the right-hand side. So we're going to end up with 340 minus Vs equals to 340 multiplied by 680 divided by 75.5555. Okay, so and then I don't want to use my calculator just yet. Okay, so now I'm going to quickly take this over to the right-hand side because I want it to be positive. And then I'm going to bring all of this over to the left-hand side. You can do this in your own way, hey guys. If you're a bit confused now, just pause the video and get Vs by itself and just make sure that we all get the same answer. Okay, and then I would go ahead and type all of that in on my calculator. Oh, and we get a beautiful answer. It's almost like they planned for this, and that's 34 meters per second. So that is how fast the ambulance is traveling. We are told that a small neutral sphere acquires a charge of that over there. Okay, so let's quickly draw that out. We have, let's draw it here. We have a sphere, and let's draw it a bit bigger. And this thing has a charge of minus 1.95 times 10 to the minus 6 coulombs. Then it says, were electrons added or removed? Okay, so what? They tell us that it was originally neutral. So when something is neutral, it means it has a charge of 0 coulombs. Okay, so that's literally what it means. It's not positive or negative. All of a sudden, it acquires a charge of negative 1.95 times 10 to the minus 6. So it becomes negative. So how does something become negative? Well, we know that electrons are negative, right? So did they take electrons away or did they add electrons? Well, they added electrons because this thing is now becoming more negative and electrons are negative. So we can say that electrons were added to. Then it says, okay, how many electrons were added or removed? So this formula that we need to use is not actually on the formula sheet, but it goes like this. The number of electrons is equal to the charge, or the change in the charge, divided by the charge of an electron. Okay, so the number of electrons, so N is the number of electrons. Delta Q is the, like, how much charge was added or removed. So how much charge added or removed. And then QE is actually a constant. I'll show you what that is now, but it's the charge of an electron. Charge of electron. And so I quickly took this table that you guys get on your formula sheet. The charge of an electron is this one. It says here magnitude of the charge of charge on electron is this one over here, but an electron is actually negative. So it's actually negative 1.6 times 10 to the minus 19, but they've just got the magnitude, okay? But its actual charge is negative. So if we had to go now work out the number of electrons, so how much did the charge change by? Well, we can say the charge final minus the charge initial, because that's what change means. So the final charge is now this, so minus 1.95 times 10 to the minus 6 minus 0. Its initial charge was neutral, so that's 0. And then the charge of an electron is negative 1.6 times 10 to the negative 19. If you had to go and work this out, and we round off to 2 decimal places, we are going to get 1.22 times 10 to the power of 13. That is how many electrons that have been transferred, or how many were added. So we can say here, added. Now I'll give you a guideline of how to remember the definition of electric field. We know that, okay, so there are two formulas for electric field on our formula sheet. There's the KQ over R squared, but that's not the one that we're going to use when we try to remember the definition. The one that we're going to use is this one. And this one is going to give us, it's going to help us to sort of remember the definition. So it's going to have to be something to do with force per charge. It's that one, the one that goes with force per charge. So if I had to go put the formal definition, it would be this. It is the electrostatic force, okay, there we see it, experienced per, whenever they have a line over here, that's like a divide line, that's per, and then it's per unit, positive charge. Okay, so this is charge, and for some reason scientists all over the world have used the word positive. So we always pretend that when we're working out electric field and we're looking at a random little place, we always pretend that that thing or that area is positive unless they tell us it's a negative charge. Okay, so we use the word positive charge, and then should be placed at that point. Okay, so there's the definition. And then this last question says, calculate the magnitude of the electric field at a point which is 0.5 meters from the center of the charged sphere. Okay, so we're not going to use this formula now for these types of questions. We're going to use this one over here. So let me just write that down. And so what we have is a little charge, or a big charge actually, which was negative 1.95 times 10 to the minus 6, and then 0.5 meters from that, 0.5 meters from that, we have a random little place. And I'll just call that x. X can just be a random little place, which we will pretend is always positive, because that's the definition. If you don't know what it is, it's just a random place. We pretend that it's positive. Now this question says calculate the magnitude. Okay, so that just means we don't need to worry about the direction. We just need the size of the electric field at a point 0.5 meters from the center. Okay, so we'll use this formula. We know that K is a constant, which is found on our formula sheet. The charge of this thing over here is 1.95. Remember, with this formula, we don't put the negative on the calculator. We don't put the negative in the formula, okay? and then we say the distance, which is 0.5 meters. That's the correct unit. And then we must always remember to square that. And if we had to go work this out, we'll get 70,200 Newton per Coulomb. That is the units of electric field. It's Newton per Coulomb. If you ever forget that, you can use this formula again. Whoops, let me do that better. So it's Newton, because that's what force is, and then Coulomb, because that's what charge is. Okay, so that can help you to remember that. In this question, they say that 2-point charges Q1 and Q2 are fixed 0.02 meters apart. The magnitude of the charges are the same, and Q1 is negative. Okay, so that means Q1 is negative, but it doesn't necessarily mean that Q2 is also negative. But Kevin, I thought they said they have the same charge. No, they just said that the magnitude is the same, so the size. So for example, if this one's -5, this one might also be -5, but it could also be +5. As they're just saying the magnitude is the same, okay? So let's say, let Q1 equal to -x, then Q2 could be x, or it could be -x. Okay, so we're not quite sure about that, so I'll leave that for now. But we know that Q1, let's say that that's -x, for example. Or let's just say x for now. I'm actually thinking, what should we do? Okay, for now, let's just remember Q1 is negative. That's all we're going to remember for now. Let's not introduce any x's right now. So Q1 is negative. Great. Now it says that a small charged sphere with a charge of -1.95 times 10 to the -6 is placed at point P. Okay, so we're placing the sphere over here, which has a charge of -1.95 times 10 to the -6. We're going to place that over there. And we're going to place that at point P, which is 0.03 meters east of Q2. The sphere at point P experiences a net force to the west. Okay, now I'm going to try to convince you that Q2 has to be positive. How do I know this? Check this out. If this one is negative, which it is, and this one is negative, which it is, because there's a negative, then what would Q1 do to P? What would it do? Would it pull it to the left, or would it pull it west, or would it push it east? If Q1 is negative and P is also negative, they would repel each other, because if things have the same type of, if they're both negative, they will repel. So that means that Q1 is going to push P to the right. But they tell us that the overall force acting on P is to the left, because it's west. See that? So how can P still move or still want to go to the left, even though Q1 is pushing it to the right? That would only be possible if Q2 is positive, because if Q2 is positive and P is negative, then Q2 has the ability to push it or pull it to the left. Because if this one's positive and this one's negative, then they will attract each other. So Q2 has to be positive. You might need to just pause the video and give this thought for yourself, but what you should find is that Q2 has to be positive. Okay. So Q2 has to be positive, and Q1 is definitely negative, because they've told us that. So they tell us that the overall effect is 1.38 newtons. So what we can now do is the following. We can say that we can choose a direction as positive. So I'm going to choose left as positive, because they gave us that the overall answer is to the west. And then we can say that the 1.38 is going to be equal to the force of Q1 acting on P. Or actually, let's do this. What would Q2 do to P? Would it pull it left, or would it pull it right? Would it pull it left, or would it push it to the right? Well, because it's positive and P is negative, it would pull it to the left. So that's going to be a positive value. So we can say FQ2. Then we can say minus F of Q1. The reason I'm saying minus is because Q1 and this one over here, P, they are both negative. Okay, so Q1 is going to push P to the right-hand side, but we said to the left is positive. That's why I'm going to make this one a negative. Okay? As I said, you might just have to pause and think about this yourself, but now we're just going to go fill in the formula. So remember that the formula for force goes like this. KQ1 Q2 over R squared. And so what we can then say is that 1.38 is equal to, now we're going to go fill in the formula for Q2 acting on P. Sorry, I should have put here acting Q2 on P and then Q1 acting on P. So Q2, well, let's go fill in the formula. 9 times 10 to the 9. I'm using this formula now. And so we're busy looking at Q2 now, which we don't know what it is, so we'll just say Q2. Okay, and then we can fill in the size of this one. But remember, we don't put the negative on the formula. We leave it as a positive. And then the distance between those two is 0.03 and then squared. Remember to always say squared. Oh, I've actually run out of space. Let me rather move this up over here. Okay, and then we're going to say minus. Now I'm going to go fill in Q1. So that's going to be 9 times 10 to the 9 multiplied by... Now Q1 and Q2 are the same. Yes, the one's negative and the one's positive, but we've already taken that into account. So I'm not going to put a Q1 here, because then I've got two unknowns, Q2 and Q1. So I'm actually just going to call this one Q2 as well, because it's the same size. Let's just write that a bit better, Q2. And then this force is also going to be 1.95 times 10 to the minus 6, well, that charge, sorry. And then the distance between, now be careful, the distance between P and Q1 is going to be 0.05 squared. So what I'm going to do now is I'm going to take this number, and this number, and this number, and I'm just going to quickly type those all in my calculator. So it gives us quite a big number. So what I can now do is I can say 1.38 equals, now that's a big number, so 195 with 5 zeros, 1, 2, 3, 4, 5, and I can say Q2. See? Now what I'm going to do is take these three numbers and quickly type that on my calculator. And so that's going to be 702, and then 1, 2, 3, 4, and then I can also say Q2. And now I can actually just go and solve this equation over here for Q2. So I'm just going to combine both of these along. And so that's going to give us 1.38 equals to 1248 and then 4 zeros, Q2. Okay, and now to get Q2 alone, you're going to have to say 1.38 over 1248 and then 4 zeros, 1, 2, 3, 4. And so Q2 is going to be 1.11, if you round off to 2 decimals, times 10. Let me write this a bit bigger. Sorry, guys. So we can say where can I write this? Here, Q2 is going to be 1.11 times 10 to the negative 7 coulombs. Hey guys, so with this one, there are quite a lot of questions that we're going to do. I'll quickly show you. So this is the first slide. Then we're going to be doing this one. Then this one, and that one. I just couldn't fit everything on one slide, but here we go. So the first one, okay, so let's see what they say. They say that a battery in the circuit shown below has an EMF of 12. Okay, so that's a constant value. That is what the battery actually says on the battery. Like if you had to go buy that battery in the shop, it would be a 12-volt battery. Right? But when we put it into the circuit, it will probably not give us 12 volts. It'll give us like 11 volts or something like that, because some of the voltage is going to be lost because of the internal resistance. Okay? So switch S is open. Okay, so nothing is happening because the electricity cannot flow because that switch is open. So it says write down the reading on V1. So when nothing is flowing and you have a battery, okay, whether it's got a resistor inside it or not, let's actually go put a little resistor if you guys want to, so we can put some dotted lines here. And then let's go put a little resistor. And okay, so we've got this and we've got this, and then you've always got a voltmeter connected across the battery. Okay, and that's always this guy here. Now, that voltmeter will always read the EMF if there is no current flowing. If there is no current. So that V1 is going to be reading 12 volts because that's a 12 volt battery. But for V2, let's quickly see what will happen at V2. And then typically, if you have any other voltmeters connected anywhere else in the circuit, those voltmeters will typically have a value of 0. Okay, so for this one, we will just say 0 volts. But if it's the voltmeter that is connected across the battery, then that one will always read the EMF of the battery. The switch is now closed, and the reading on the ammeter is 1.2 amps, and the power given off or dissipated in resistor X is 5.76 watts. It says define the term power. And there's the definition of power. It is the rate at which work is done or energy is transferred. So we know that power is equal to, or we can actually just simplify it. We can say work divided by time. So it is the rate. Rate talks about time at which work is done. Okay, that can sort of help you to remember the definition. Next part says calculate. And we must remember all the things that they told us. They told us that the ammeter is 1.2 amps. That's important. So it says calculate the resistance of resistor X. So we know that there are 3 formulas for power in electricity. There's this one, and then that one. Now, if you know the way a circuit works, we know that all of this, so from here up to here, okay, so once the electricity gets here, then some of it would go, whoops, let's get a different color. Some of it would go this way, and some of it would go that way. So because it has to split, that means we are now in a parallel section. So maybe some of it will go this way, and then the rest would just go up here. But then what would happen is that they would come together again over here, and then they would carry on like this. So everything that I have done in yellow, that is part of the main circuit. And then all the stuff in red, that is where they split up. Well, let me actually do it in different colors. So maybe some of the electricity would go this way, up to there. And then some of it would go this way. So we can put a little line there showing arrows. So that area there, because it had to split up, this whole area here is a parallel section, whereas this part here in yellow, that's part of the main circuit. So it's almost like this is the big river, and then when it gets over here, some of the water goes this way and some of the water goes this way, but then it joins together again over here, and then it carries on like that. So what am I on about? Like, why am I telling us this, or telling you guys this? Because if we know the current over here, then we can see that because it's yellow and yellow, we know that the current will also be, we know that the current over here and the current over here will be the same. So the current going through this resistor is also going to be 1.2 amps. So we could just go use, what did they want us to find? The resistor. So we could use this formula here. So we could say that 5.76, which is the power, is equal to 1.2 squared, which is the current, multiplied by R, which is the resistor. And then you could get R by itself by saying 5.76 divided by 1.2 squared, and R would be equal to 4. So that would be 4 ohms. 4 ohms. So let's just remember that for later. Okay, next one. Calculate the total external resistance in the circuit. So that means we're going to have to go get this resistor, which we already know, and then all of this, and then this one over here. Now, pay careful attention, guys. What a lot of you might do is you'll say, oh, these 3 are all in parallel, and then you're going to go say 1 over 2.4 plus 1 over 6 plus 1 over 6. But that is not correct. Look carefully. Can you see that these 2 resistors, they are part of the light blue part, right? So they are actually in series together. So what we need to first do is add those two together to get the resistance of this blue stream, or this blue part. Okay, so that blue part is going to be 6 plus 2.4, which is going to be 8,4 ohms. Then we can combine that 8,4 together with the 6 in parallel. So let's go write out the formula for parallel. So it's 1 over R1 plus 1 over R2. So we can say 1 over R parallel is equal to 1 over 6 plus 1 over 8,4. And if we have to go work that out, we get 2 over 7. And then we flip it around to become 7 over 2, which is the same as 3,5 ohms. Now that's not the final answer. That's just the parallel part. So now that's done. Now we can add that together with this resistor over here. So the R total, or the R external that they're talking about, would then be 3,5 plus 4, and so that's going to be 7.5 ohms. So that is the total external resistance. Okay, now we need to calculate the reading on voltmeter V2. Now there are a number of different ways that we can do this. So let me quickly, so V2 is pretty much only connected across the 6 ohm, because if you had to extend this, it's connected up to there, and then if you extend this one this way, we could like let it stop there, for example. So we know that it's definitely measuring. I mean, you could extend it further, but then it's just going to start getting weird. So we know that it's definitely measuring across the 6 ohm resistor. Okay, so it's connected across that. So we need to go and somehow figure out, because if we want to work out the voltage, we know that voltage is current multiplied by resistance. We need to know how much current is going through this part of the circuit. So when this 1.2 amps arrives over here, some of it is going to go this way, and some of it is going to go that way. And we need to try to figure out how that's going to work. So there were these formulas that we used to use in grade 10. Well, not all schools did it, but a lot of schools did them, where if you know the current, the total current arriving over here, then if you know the different resistors, you can somehow use fractions to work out how much of the current is going to go this way and how much of the current is going to go this way. Okay? And that formula goes like this. You can go I of a specific branch. So let's say, for example, you want to know, let's call this, for example, branch number 1, and let's call this branch number 2. Then if you want to know how much current goes into branch 1, you can just say R parallel divided by R1 multiplied by the total current. If you want to know how much goes into to the second branch, you can say R parallel divided by R2 times by the total current. Okay, so if we want to know how much current is going to go into this branch, all that we need to do is we need to say I2 is equal to R parallel, which we calculated as 3,5, over this resistance in this. So when I say R2 over here, I'm talking about all the resistance in branch number 2, which is the 6 and the 2.4, which is in series, remember, like we said earlier. So that's going to be 8.4, and then we're going to multiply that by the total current, which is going to be 1.2. And so if we had to go work out that, we should get 0.5 amps. 0.5. Okay, so that means that 0.5 amps is going to go this way, and the remainder, which would be 1.2 minus 0.5, which is 0.7 amps, would go this way. So 0.7 amps this way, 0.5 amps would go that way. So now we know how much current is flowing through this resistor, so we can work out its voltage by using V equals to I times R, and so I is 0.5, and the resistance is 6, and so that's going to give us 3 volts. And that's for V2, so we can say that V2 is 3 volts. Now, some of you might not have liked that. I have picked up in the past that some students are not aware of those other formulas that I just showed you, like how much current goes this way and how much current goes this way. So let's do an alternative method. What we can go do is we can go work out what this voltmeter is going to be. Now remember that this voltmeter, V1, it will measure the EMF when the circuit is switched off. When the circuit, or let's say when the circuit is not flowing. Okay, it measures the EMF. But when the circuit is flowing, then it measures the external voltage. Some people like to call this the terminal voltage. So it measures the voltage that's being delivered to this one, this one, this one, and this one. Okay? So that is what V1 measures. So let's go measure what V1 is going to be. So we can use V is equal to I times R. Because V1 is measuring the external, we must use the external resistances, which is this one, this one, this one, and this one. But we already combined all of those in the correct way because some of them are in parallel, and we got 7.5. So we know that the total current in the circuit is 1.2, and we know that the total resistance in the external part is 7.5. And so if you had to go work out V1, you should get 9 volts. Okay, so we went to the shop, we purchased a 12-volt battery, but only 9 volts is actually being delivered to the external circuit. Obviously, 3 volts is being lost in the battery itself. Okay, so now what's interesting is that, okay, so we know that there's 9 volts being delivered to the external part of the circuit. We can quickly go work out how much voltage is being used over here. So we know that V is equal to I times R. And we can say this is for resistor X, so we can say Vx. So we know how much current is flowing through there, it's 1.2, and we know that the resistance for that one is 4. And so that's going to give us 4.8, not ohms, Kevin, volts. So 4.8 volts is being used over here. So how much voltage is left over? Well, if we say 9 minus 4.8, that's going to give us 4.2 volts. So there is 4.2 volts left over for this part. But remember that this part is in parallel. So we know that voltage in parallel is the same. So we know that the voltage across this branch will have to be 4.2. And then the voltage going through all of here would also have to be 4.2. Not 4.2 for this one and 4.2 for this one. 4.2 altogether. Okay, 4.2 volts altogether. So what we could now do is we could work out the current that is flowing through that part over there. So we could say I equals to V over R. And we now know the voltage in that part is 4.2. The resistance is 6. And that'll give us 0.7 amps. Okay, so this will be 0.7 amps. So we know from earlier that the total current in this part of the circuit is 1.2. We've just calculated now that 0.7 amps goes this way. So that means that 0.5 amps would go this way. 0.5 amps would go this way. So this is now good because now we know how much current is going to flow through the 6 ohm resistor. So now we can work out how much voltage or V2 will be, because remember we said just now that V2 is connected across the 6 ohm resistor. And so we know how much current is now flowing through the 6 ohm resistor at 0.5, and we know that the resistance is 6. And so we can say V is equal to I times R, and we can say that the voltage is equal to the current multiplied by the resistance, which is 6, and that should give us 3 volts. So I've now showed you guys 2 different ways of how you could do this one. I'm hoping that for most of you, you would find one of those understandable. And here's our last part. So it says that the length of wire of negligible resistance is used to connect point P to point Q in the circuit. A length of wire of negligible resistance. Oh, I see. Okay, I was reading that weirdly. So they're going to take a piece of wire and they're going to connect it from point P to point Q. Okay. So they're going to connect a piece of wire. Now, you got to understand that that's going to affect absolutely everything. Let's see how this would work. We know that the electricity flows this way. It goes down here. And then some of it would go this way. Okay, well, let's do that in a different color. Let's stick to the way I used earlier. And then we said that some of the current will go this way. And then through here. Whoops, sorry. Just up to there. And then we said that the rest would become yellow again. Well, that color. Okay. And then we said that some of the other current would go this way and go here and go here. But now, remember, electricity is always looking for the path of least resistance. So when this current over here reaches this point Q, all of it is going to go through here because there's absolutely no resistance. Okay, so it's going to go to there, and then it will join up. Okay? So what we've effectively done here is we've eliminated this little resistor. So the total resistance in the circuit is going to become less. So R external will decrease. So think about what that does. What will that, if your resistance, your total resistance in the circuit becomes less, what does that do to the current, which is like how fast everything will flow? Well, if you've taken away a resistor, then everything is going to flow faster. So the total current, the current will increase. Now, if you've watched some of my other videos, I would have explained how an increase in current is going to make your voltage in the battery much higher, and so V1 is definitely going to decrease. But let me try to explain that a bit. So we know that your EMF, when you buy it from the shop, it's going to be used up on the internal part of the battery, which is this part over here. We call this the lost volts. And then the rest of it is going to be used on the outside of the circuit, where some of your teachers might call this terminal voltage. Terminal voltage. Let me write that a bit better. So you can either call it external or terminal. Okay. Then what I'm going to do is I'm going to change this formula to I times R, and then I'm going to keep this one as V external, which is actually in this question, it's this one here, which is V1. So let's go change that to V1. So we want to sort of see what's going to happen to V1. So if I go get V1 by itself, I end up with EMF minus IR. Now, luckily, this is a constant, so we don't need to worry too much about that. It won't be changed. This is a constant. Small r is a constant because it's the way that they make the battery in the factory. The big R can change sometimes. I mean, we can change that by just knocking this resistor away. But this little R never changes because it's the way that they made the battery. We said that this I is going to increase. Okay, so this number is going to go up. So if you just had to do the maths, this stays the same. This number's going up, and this stays the same. So you might need to pause the video and think about that, but if you just do the maths carefully, V1 is definitely going to go down. So V1 is going to decrease. The first thing I want to mention here is that we are going to be doing more than these two questions over here. I just couldn't fit everything on one page. So here's 9.1 and 9.2, then 9.3, 4, and 5, and then 9.6. Okay, so let's begin. So it says that we have a simplified diagram of an AC generator. All right, so this is an AC generator connected to a 25 ohm resistor. The coil rotates anti-clockwise. So we can see in the diagram that it's rotating anti-clockwise. The first question says, name the component that distinguishes this generator from a DC generator. Okay, well, we know that if we use slip rings, then we know that that is AC, right? And then if we use a split ring commutator, then that is DC. So a split ring is the one that literally has a split. See, there's a little gap over there. But when you have these two little rings like that, then we call it a slip ring, and so that's AC. So it says name the component that distinguishes this one. We will say that it's the slip rings. Then it says, in which direction will the induced current flow in section XY? Choose from X to Y or Y to X. Okay, so remember guys, generator, we use the right hand. And then if it was a motor, then you would use your left hand. So you're going to use your right hand, okay? Now obviously it's difficult for me to show this to you guys without putting all these like diagrams, but yeah, it's complex to find the right kind of diagrams and stuff. But this is an exam question, so you guys should understand your basics by now, and this question should just be like a practice kind of thing. So you're going to be using your right hand, and okay, so depending on how you do it, but remember that your index finger will always point from north to south of your right hand. Then your thumb would show the direction of rotation. So if you were looking from this point over here and you were looking towards this structure, what you would see, let me try to draw it for you. You would sort of see the north over here. Well, there's your north magnet, and then there's your south. This is your north, this is your south, and then you would sort of see something like that, where this would be X and this would be Y. So, but I want to get it more horizontal. Give me a second. So you would actually be just seeing something like that. So this would be X and this would be Y. Now, okay, so your index finger is going to point from north to south, and XY is moving downwards. You can see it's about to rotate downwards. So your index finger would be pointing from the north to the south. Then your thumb is going to point downwards, and then look at what your middle finger is doing. Your middle finger, if you're doing this correctly, it should be pointing towards you. Okay, it should be pointing towards you. And so the current would be flowing towards you. So that would be from Y to X. Alright, so the next part says, define the term RMS potential difference. Okay, so it's root mean square potential difference. And so there I've added it at the bottom. It is the AC potential difference which will dissipate the same amount of energy as the equivalent DC potential difference. I wouldn't worry too much about that one. Yeah, that one's a bit of a weird definition. Okay, so 9.4. I see that I didn't have the marker location, so I've added them in now. So there they are. Okay, so they want us to calculate the RMS current in the circuit. So we know that current is equal to V over R, okay? But now with AC, we don't know whether we should use this as the values, for example, the voltage. Like, what do we use? Well, remember, that's why we use RMS. So whenever we have AC, which is alternating current, we use RMS values. So if you want to find the RMS current, then you need to use the RMS voltage. Luckily for resistance, you don't get a RMS resistance, you just get a resistance. Okay, so we need to go calculate the RMS voltage. Now, we know that the maximum voltage is 100. And so for that, we can use the formula on our formula sheet, which goes like this. So we can say that VRMS, whoopsie, so VRMS is equal to the Vmax, which is this 100, over the square root of 2. So that's going to be 100 over the square root of 2, which I'm not going to round off, is 50 square root 2, and that's volts. So now we can use this formula up here again. So we can say that the IRMS is equal to 50 square root 2 over the resistance value, which we said was 25. And so if we had to work that out, and if we round off to 2 decimal places, we're going to get 2.83 amps. 2.83 amps. The next one says calculate the average power dissipated in the 25 ohm resistor. And so from the formula sheet, these are the different formulas that we can use for power. So I think, I mean, you can choose whatever one you like, but I think this one would be good because we already have the RMS current from the previous question. So we can then just say that the P average is equal to I squared RMS multiplied by R, and so that's going to be 2.83 squared multiplied by 25. Notice that the R doesn't ever have an RMS. R is just R. And so if you had to go work this out, you end up with 200,22 watts.
Now, sometimes I check on the memo just to make sure that my answers are corresponding, because I can make little mistakes sometimes. And I did see that depending on which of these formulas you used, you might not get 200,22. Some of the formulas actually give you 200 watts exactly. Some of them gave you 200,11. So those are the different answers that I saw. Okay, so using different formulas can give slightly different answers, but they do allow for that on the memo. On the memo, it says this answer, or this answer, or this answer, for example. In the last question, they tell us that the speed of rotation is now going to be doubled. Okay, so remember earlier on they were spinning a generator. Now they're going to spin it twice as fast. Okay, so what they then want us to do is to redraw this graph, which is the one we had from the previous part, and they want us to see what that graph will now look like, because they are now spinning it twice as fast. So we need to go back to Faraday's law, which is this one here, and what we need to understand is that we're not changing the number of turns, and we're not changing the magnetic flux. Remember that this symbol here, from grade 11 is equal to BA cos theta, where B is the strength of the magnets. So that's like your strength of magnets. A is the area of the loop, and then theta's just got to do with the rotation. So we're not changing any of those. All that we're changing is the time. What are we going to do to the time? Be careful, we're not going to double the time, we're actually going to halve the time for each rotation. Because remember, if you go faster, the time becomes less. For example, if you can run 100 meters in 20 seconds and someone else can run 100 meters in 15 seconds, they are faster than you. So with time, we are actually going to be halving that, okay? So we're going to be halving that. So if you divide this entire thing by a half, you're actually going to end up doubling this entire parameter. For example, if you say 1 divided by a half, that actually gives you 2. And if you say 2 divided by a half, that actually gives you 4. So when you divide something by a half, you're actually multiplying the entire thing by 2. So you're making it bigger. So we know that all of these values are going to double. So this 100 is going to become 200. And this minus 100 is going to become minus 200. But these time values are also going to half. Okay, so, all right, so it's still going to start here at 0. Now, this value is now going to be 0.012. It's going to be like somewhere over here, but its voltage value is going to be 200. Okay, so we've taken care of this point. Now, this point here, if you divide that by 2, that's going to be 0.025, but it'll still be at 0. Okay, so we've taken care of that point. Then this one over here, if you divide that by 2, you're going to get like 0.036 or something like that, which would be somewhere over here, but that's going to be at minus 200, so that's going to be over there. So we've taken care of that one. And then 0.1, if you divide that by 2, you get 0.05, and that's going to be there. And then everything's just going to repeat. So we're going to get that one cycle up to there, and then everything's just going to repeat. So there. So something like that. So what they would be looking for in the memo is that you're hitting 200 and you're hitting minus 200 and you've completed 2 complete waves instead of only having 1 complete wave. Please note that this is not the only question we're going to be doing for this one. I broke it up into 4 different slides, as you can see over there, just so that we have more space. Okay, so here's the first one. It says that the relationship between the frequency and the maximum kinetic energy of photoelectrons emitted from cathodes M and N of different photoelectric cells is investigated. The graphs below have been obtained. Okay, so this is definitely a photoelectric effect kind of question. And the first question says, define the term threshold frequency. And so there we have it. It is the minimum frequency of light needed to eject electrons from a metal. Remember that if you have a metal, okay, so let's say this is a metal, we know that this metal has electrons, right? And if you could take some type of light, okay, so let's say this is our light, like a light bulb or something, and that light is going to travel towards the metal. And remember that this light has a specific frequency.
That's not the threshold frequency. That's just the frequency of the light. Now, if you want this light to be able to take these electrons and allow them to be released, then the frequency of this light needs to be large enough. How large exactly? Well, each metal has its own threshold frequency. So it's something about the metal, not the light. So each metal has its own threshold frequency. So let's say, for example, that this metal has a threshold frequency of 10. Then that means that if this light has a frequency of 9, then nothing will happen. But if this metal has a frequency of 10 or more, so like maybe 10 or 11 or 21, then it is large enough to be able to cause these electrons to be released. Okay, so it is the minimum frequency of light needed to release electrons from a metal. Okay, so in this example, the threshold frequency would be 10. And that would then be the minimum frequency that the light would need to have to eject electrons from a metal. Here's the next question. Okay, so I found that this question was quite interesting when I looked at it now. I felt like something was a bit weird, and maybe you'd pick up on this yourself, but normally when they give us a frequency kinetic energy graph, we normally have the frequency on the x-axis, and we have the EK max on the y-axis, and then the graph normally does something like this. It usually goes like that, for example. Okay, but they've just flipped it over, so everything's pretty much the same. The part here, when it goes through the x-axis, or when it goes through the axis that has the F, or the frequency, that is normally called the threshold frequency of that particular metal. So it's going to be the same in this question. This is going to be your threshold frequency over here for cathode N, and then this will be your threshold frequency for cathode M. Okay, so that's your threshold frequency. So we'd say threshold, and then this one here would be the threshold. Okay. So I just wanted to get that out the way before we go to the next one. So it says, how does the maximum kinetic energy of photoelectrons emitted from cathode N compare to that of cathode M when light of a frequency greater than 10.4 is shone on each of the cathodes? All right, so if you look at this carefully, cathode M requires 10.40 times 10 to the 14 hertz for an electron to be released. And now, okay, whereas cathode N only needs 5.16 times 10 to the 14. So this one needs less energy to release an electron. So I'm going to just write that so we can make a little summary here. Cathode N needs less. This isn't what you're going to write in the exam. This question just wants you to say greater, smaller, or equal to, but I want you guys to have an understanding of it. So it says cathode N needs less, that's what we're saying. Cathode N needs less energy to release an electron. Okay? So if you take a certain amount of energy, okay, and you shine it on M, and you shine it on N, and this energy is larger than 10.40, then we know that both of these cathodes, or what did they call them? Yeah, cathodes, they're both going to release electrons because the energy or the frequency of this light that they're using is larger than the threshold frequency for both of them. So they are going to release electrons. But the electrons in cathode N will travel much faster because there will be more energy left over. Because let me try to remind you how this all works. Remember, if you have a metal, so let's say you've got this metal, and this metal is metal N, and then you've got this light that is shining onto the metal N. Let's say the frequency of the light is 10.5, because they said that it's a little bit larger than this. So let's say it's 10.5 as an example. And that shines onto the metal.
Now, 5.16 of this energy is going to be used just to release the electrons. Remember, that's the threshold frequency. So that is how much energy will be used just to release the electrons. Okay, so 5.16 times 10 to the 14. So how much energy will be left over after that? Well, the leftover would be 10.5 times 10 to the 14. Okay, I'm just going to say 10.5 minus 5.16. You guys know what I mean, right? 10.5 minus 5.16. And if you had to work that out, you get 5.34. And remember that 5.34 is the leftover energy that will be the kinetic energy of those electrons. Because remember, those electrons are going to move away and they're going to have kinetic energy. And that kinetic energy is going to be the 5.34. Now, let's see what happens if we use metal M instead. Then what happens is you still have the same light bulb, and it's also shining 10.5 times 10 to the 14, and it's now shining towards metal M. And metal M has a threshold frequency of 10.4. So I'm just going to say 10.5 and 10.4. So if you minus those two, 10.5 minus 10.4, you get 0.1. So there will only be 0.1 left over for the kinetic energy, because more energy had to be used just to release or to eject the electron. Okay? So the kinetic energy is definitely going to be larger in metal N. So we can say greater. Because they said, how does N compare with M? We can say it's greater. Moving on to this question now. So this one's for 5 marks, so it's definitely going to have some calculations. So what I did is I just went and got the most popular formulas that we have on our formula sheet, and I also got Planck's constant over here. Now, sometimes they say on the formula sheets, they only say 6.6. Sometimes in the IEB specifically, but many times with the CAPS documents, it says 6.63. So when you are in your exam, just check for which one is just obviously use that value. So what we can do here for this question is we could just try to use this formula over here. Now, we're going to have to expand this E into HF, so we can say HF, and then we're going to have to expand this W0 into HF0, so HF0, and then this one we can just leave it as EK max. So we'll have to use this one because it's on that one's line, if you look carefully. It's meeting at that point over there. So this F is going to be this F, and then the threshold frequency, which is the 10.40 times 10 to the 14, that's going to be the threshold frequency. The kinetic energy max is going to be, see if you look down here, that's going to be 23.01 times 10 to the minus 19, and then the only unknown would be this F. Because H is obviously a Planck's constant. So what we can do is we can go fill that in as 6.63 times 10 to the negative 34 times by the frequency, which is what we are trying to find, which is Fx. And then we can say 6.63 times 10 to the negative 34 times the threshold frequency. Okay, I'm going to run out of space. And there we've got that plus the EK max, which is then going to be 23.01 times 10 to the minus 19 times 10 to the minus 19. And so we're just going to have to somehow try and solve for this one now. So I'm just going to multiply and add all of these things over here together. And so what we end up with is that. And then I'm not going to round this one off. So it's 2.99052 times 10 to the negative 18. And then to get Fx alone, I'm just going to move it over here. You're going to take that value, and then you're going to divide with 6.63 times 10 to the negative 34. And that should give us a final answer of 4.51 times 10 to the power of 15 hertz. And now for this last question, they say that the experiment is now repeated for cathode M using light of frequency Fx. Okay, so we already worked that out, but of a higher intensity. Okay, guys, so remember what happens when you have a higher intensity. Let me quickly explain. So if you have a metal and you've got electrons, okay, and you've got a light source. Now that light source is busy releasing light. and that light has a certain frequency and intensity. Okay, so the frequency is like how many little waves can you see, but the intensity is how many photons are there. So see, I've got all those little photons. Each of those little things is called a photon. Okay, now that would be a high intensity light, whereas a low intensity light would be more like this. See, there's less of them. Okay, so that would be, so this would be, or let's say this would be low intensity, and then this one here would be high intensity. Doesn't mean high energy. That's not the same thing. The energy for these two things can be exactly the same. Maybe this one here, this photon has 9 joules of energy, and this one can also have 9 joules of energy. But that's what intensity is, okay? It's like the number of photons. So we're going to repeat the experiment, but we're using a higher intensity. How will each of the following be affected? Choose from increase, decrease, or no effect. Okay, so the y-intercept of the graph. Well, this y-intercept, remember, that is the threshold frequency. That is the threshold frequency. And remember that the threshold frequency is based upon the metal, not the light. It's based upon the metal, not the light. So this will not change at all because we're changing the light intensity, but that doesn't affect the metal, doesn't change the metal. The number of photoelectrons emitted per unit time. Okay, so this one's definitely going to increase, but let me try to explain. So let's say, for example, we were using a low intensity light. Okay, so look at how many of these little photons there are. See, there's not that many, right? So each time one of those photons hits this metal, 1 electron will be released. So each time one of these photons hits, 1 electron will be released. So what would happen if you have to increase the intensity? Well, what that does, or what that means, is that there will be more photons arriving, or it'll be happening much faster. Okay, there will be more photons arriving, and that means there will be more electrons that are going to be emitted. So this one is definitely going to increase. Okay, now what happens to the energy of the photo? Now here's where some students will say increase, but you got to be careful. What we said was that both of these lights have the same frequency or the same energy. You see, they both have 9 joules of energy. That was just a made up number, but I'm trying to show you that the energy or the frequency is exactly the same. So when this one, which has 9 joules of energy, when that one hits the, okay, I need to show you guys something else. Just give me a second. Okay, so let's say we've got a light source. Okay, so let's say we've got a low intensity light source. I'm just going to draw it as straight lines like that. So that's low intensity. And let's say that each of these have 9 joules, okay? And then there's a metal over here. Then I'm going to draw a high intensity light. Okay, so that would look more like this. See, there's a lot more photons. But let's say that the energy or the frequency of the light is exactly the same. Okay, so let's say that this metal has a threshold frequency of 5. Let's use hertz instead. Doesn't really matter. This is just an explanation. But let's say this is 9 hertz. And let's say this metal has a threshold frequency of 7 hertz. Okay, so what that means is that this, let's start with this one. This 9 hertz photon, so this photon is 9 hertz. It's going to hit the metal. And because the frequency is large enough, an electron will be released. Okay, so how much hertz? Okay, so 7 hertz is going to be used for, or you could think of it as joules if you wanted to, but 7 hertz is going to be used to release the metal, and how much would be left over for release the electron, and how many hertz would be left over? Well, that would be 2 hertz would be left over, and that would go into the kinetic, that would make the electron move, okay? Now, if you use a high intensity light, this is still going to have 9 hertz. So every single time that an electron gets released, it's also only going to be able to use the 2 hertz
of frequency that is left over. So whether we use a low intensity light or whether we use a high intensity light does not change the energy of the electron that is released. It only makes more electrons get released. Okay? If you use a higher intensity light, more electrons get released, but it doesn't make them faster, or it doesn't make their kinetic energy more. So this one would also be no effect.